Alright, let's get going. If you're not familiar with how I do things, okay, so let's get going here. We left off doing some math for see this diagram here? This is how we're going to lay out the data for PAINT5D, for how all of the tile data works on a 512 by 512 bitmap. So this is the partitioning on a 512 by 512 bitmap. So you can see the 512 right here. Assume that everything is square, unless otherwise noted. So you can see that I label this as pixel data partitions, and then also here you can see what the artist sees, and the artist just sees pixels. They don't really even see a division, do they? I guess what we should do is, you know, maybe that's a little bit, maybe that's a little bit too much detail. They just see some pixels or something, but not the. So really what the artist sees is what I drew earlier there was a whole bunch of noise, you know? So let's actually kind of rephrase this, you know? This is what they really see. And if you want more information, you know, at vid integer ID, 0 hours, 2 minutes, and 5 seconds. Okay. To review what's going on up here, though, what you're actually working with, the data you're working with, we have 4 subtiles within an autotile set, or an AW set, I'm calling them. So here's tile 1, the top left. Here's the top right. Here's the bottom left. And here's the bottom right. And these are the physical areas of the 512 by 512 where the data for those 4 tiles go. Now, coincidentally, in the editor, this data is going to be displayed, you know, like up here in this corner, right? And you might want to make a note of that. That they see the top left design view subtile. Okay, so they see the top left subtile, and then over here they see the top right subtile. And I don't know exactly how we're going to do it. I don't know if we're going to make any distinctive division between the tiles, or if it's just going to look like a smooth border, and you just have to say, oh, this is the same amount of data, and this is the same amount of data, and you're going to have to delineate. Actually, a hard border would actually help, but not too big of a border. Just enough of a border to see where something begins and ends, because we want the artist to actually have a visual idea of how these tiles connect, right? These tiles need to be designed in some way that they connect, because our auto generation of auto tiles can only do so much. It can only be so smart. And so we're expecting that, you know, this is going to be some edge design that the artist is going to put in, and that these edges here, going from this tile to that tile, somehow merge together gracefully. The artist is responsible for that. And these edges here, from this tile to that tile, also need to merge together gracefully. Same thing with these tiles and these tiles, these tiles and these tiles, etc., right? So what we might want to do is just make a note of these being these subtiles. And we also might actually want to, you know, rename it to something appropriate. Like, instead of calling it, well, first of all, top left, top right, and then bottom left, and bottom right. Bottom right. So subtiles, I think I have some variable names explicitly for subtiles, but right now I don't know what I was calling them. But I do feel like I gave them some type of fancy name, so I'll have to look that up later. So this is what the artist sees, right? The artist in their editor is just going to see this top left, top right, bottom left, and bottom right subtiles. Okay, so at vid iid 0068, and the time is 0 hours 5 minutes, 5 minutes and 17 seconds, or let's do 20 seconds. Okay. Okay, so let's go over this data. So why is the data in this kind of like fractally looking pattern? Well, it's kind of a mip-map pattern. If you're familiar with the mip-map, we're doing something very similar. The largest tile is actually way down here because we only have one of them, right? The largest tile fills the entire screen. So the pixel down here, this one little pixel down here, will fill the entire background here, right? And then when we're talking about the largest tiles, we need more of them, and that's why they get a bigger partition, because there's more of the small tiles, and the small tiles, you know, they just fit in little small areas in here, right? And then there's all different tile sizes in between. Now, this tile size here is going to be 4 times bigger than the tile size here, and that's why this tile size is, well, 4 times smaller, right? So as we go to bigger and bigger tiles, we get less and less of them, right? And as we go to bigger, and as we go to, sorry, so the relationship is more tiles, they're going to be smaller. Less tiles, they're going to be bigger, right? I guess that's all I needed to say. Okay, so let's work on this disaster of a code we left on Monday/Tuesday, right? We drank a lot of caffeine. The days kind of blurred together. We got a macro, astapix to diapix. So first of all, what the hell is astapix? What the hell is diapix, right? We had a little definition somewhere, and we should probably make a little index. I don't know. We could make an index somewhere. We could. We got this data. Why not make a little index here? So when we're looking at the code, maybe we want a little index view of what the variables are and what they kind of mean. So when we're looking at these, you know, abbreviations, instead of having to reference it somewhere, we can kind of see it right away. So astapix. Do I have astapix means? Astapix means. Did I not do this yesterday? Did I not? And it looks to me like I did not do this yesterday, or I have not reloaded my shortcuts. So let me look at my shortcuts really quick and see if I have this defined. And I don't. So let's take my shortcut script. Well, first let's save this, and let's document that over here. So Windows key, or not that, Windows key, arrows, and let's just go look at, well, what is astapix? What's diagpix? Diagpix is actually pretty obvious. It's the diagonal pixels. But so astapix, offset subtile pixel location. Awesome. Okay, so we can take that. We can run with that. And just say, you know, astapix. Oh god, I have a hang now, and I just started coding. God damn it. Okay, so astapix means, what does that mean? Astapix. Okay, it means offset subtile. Offset subtile. And also maybe we want to do it this way, because offset subtile, offset subtile, and then pixel location, and the location is X or Y. Okay. And that's way too big of a definition for my column limit that I have on the main file, but whatever. We'll go with that for now. And so if we do astapix, then I want to see astapix like that. Say, hey, you typed that right. Good job. Okay, if I do astapix, or astapix, or how about astpix, I just want to be like, Astapix. Where's the correction? You are welcome, right? Okay. Okay, so the next thing is, what about the diagonal pixels? Well, if we didn't do the Astapix, we probably did not do diagpix either. Diagpix? Okay, so if you type diagpix, then I also want to be able to see that, yeah, this is the celebrating NY with your community, prep your channel with NA, no thank you, stop bothering me, Twitch. So, diagpix, u plus bonds hexa, diagpixels, baseline. And diagonal pixels, what are we doing here? Diagpixels. So, let's keep a diagpix, diapix, diapix. If you type that, diagpix is the correction. Okay, and what does, let's kind of indent this as well. We might as well keep some consistent indentation. Diagpix means, what does diagpix mean, right? Diagpix means. Okay, and diagpix is diagonal. Diagonal? I don't know how to spell diagonal. Hey there. So I don't know who just popped in, but hello there. I am right now in the middle of documenting some of my variable names very meticulously into my shortcuts because I have a problem, I guess. Or, you know, Hungarian notation, apps Hungarian and system Hungarian just wasn't good enough for me, so I decided to go overkill and give all of my variables exact definitions because I'm crazy. So let's see, diagonal pixel, pixel, and this is a location, location, x or y. So we're not actually determining if that location is x or y location, it's either one. Okay, I'm gonna put this over here. Okay, so we have a little refresher of what those variables mean, and I was thinking that it'd be nice to start building beneath, you know, all my diagrams in the data file. It would be nice to kind of start to build an index of index of variable names for I don't know, terminology index, variable index, token index, identifier index. That would be X. I also might want to put like things that are used in function names as well. So let's call this identifier index. And I'm just gonna, like, as I write things, I'm gonna, as I come up with names that I'm kind of making up, I'm gonna make a little index here so that other people can reference it. So instead of me just using my personal notes, other people who are using this code base can kind of reference this index. So PAINT5D terms only. So this identifier index, used in, I don't know, terms used in, I don't know, hold on. I want to be concise, and that's why you see me keep on backspacing. Identifier index, PAINT5D, and only terms used in PAINT5D. That still seems kind of like ugly, but I don't know, I guess that'll work. So let's do this. Let's go over here, let's backspace like 4 times. 1, 2, 3, 4. And we don't have to say only terms used in, that's a little redundant. You know, terms used in PAINT5D is probably enough to communicate that that's what I mean, right? So when I say identifier index PAINT5D, I'm saying that's the terms used in PAINT5D. So as we kind of like create this index, it's going to be just terms in PAINT5D, and then we can sort that index later or maybe you want to group them by what makes sense. So astapix, offset sub tile pixel location, and that's X or Y. Right, we're not distinguishing between the two, right? And then diagpix is going to be diagonal pixels, and that's a location of diagonal pixel. No, let's not do that. Let's just say location X or Y. Because these are supposed to be kind of analogous variables. You know, astapix is the same kind of data, but it's identifies an offset subtile pixel, and then diagpix locates a diagonal pixel. So we could also take these terms here, and we could look at our diagram and be like, well, where are they in, you know, these diagrams here, right? So I might actually want to take kind of like one of these guys here and just open up another section for some more diagrams. And I found it very helpful to, in diagrams, to have like little @ symbols that tell me like what the variables are for in terms of the data layout, right? Like we have this conceptual data layout here, but we don't really know, we have a little bit of things like this thing here and this thing here, but there's other variables we're using for this diagram here that are not, we don't know what they actually represent in the diagram by just looking at the diagram. So that'd be kind of nice to have something like that. So what we're going to do is we're going to say, let's say, how could we do this? We could do something like, I don't know. Diagpix is equal to 0 right there, and then over here, you know, diagpix is equal to 128, I believe. Let's see that for a second. Yeah, for these diagpix, they are local. They are local, so that would be correct. Right, because this is a 120. This is 128 right here. Yeah, that's correct. Okay. So diagpix is 128 right here, and then over here in this section right here, we could do the same kind of thing. We could just say like diagpix equals 128 plus 64, which equals, I don't know. Let's get a calculator because I can't. If it's not an exact power of 2, I don't know. And I want to be careful. 128 plus 64. What is that? Oh, and you know, our so helpful Yahoo search. Like I like Torch browser, except for the fact that I have to do this, www.google.com. Even though I kind of configured stuff, it's still, what does it do? Oh, I say the default browser is Google, but the new tab still opens to a Yahoo search engine. I think that's what's going on. But yeah, so 128 plus 64, I should just open up a calculator, but here I am using the internet to process. You know, this is the most expensive calculator ever in terms of processing speed, right? Because I got to go over to a network, do the calculation, and then bring it all the way back. So it's like going across the world just to do a single calculation, and that sounds absurd, but here we are in the future. So, okay, so this is 92. I might want to write 92, 192 here, and then we can say, you know, equals, you know, 128 plus 64, right? So we have this this diagpix, and I actually have enough room where we can say, you know, at diagpix, and we can kind of put a little thing in front of it like that. Okay, so now we have when we're looking at this diagpix in the diagram, right, then we know what we're looking at. And when we see this in the code, we know that it refers to this diagram here. Now we have this diag x and diag p, and we know that that just means diag pix dot x, right? That's what that means, right? And same thing here. This is diag pix dot y. So we might as well take this and say that, you know, diag tx equals 128, and right, it's diagonal, so both the x and the y are equal to each other here. Right. Now, the reason why we do these two calculations here is because these are not necessarily equal to each other, and we're taking the min of them. So conceptually, when we're looking at diag pix, we're trying to look at these things here, right, to figure out what sized tiles we're using, right? So these are the smallest tile sizes here on our 3 different layers, and then the next tile size larger are these tiles. There's less of them. There's less of them. That's why they get a smaller data partition, and right, the 3 layers for that. So 2 layers here, and then a layer down here. The next size down right here, and we need to know the origin of the pixel to figure out like how we're gonna get at all these things here, right? So we have to figure out this origin pixel here depending on what size tiles we're trying to fetch. Okay, so got a nice little error here for to do finish this formula. Excellent. And I see I have a min function here, and I do not believe I wrote a min function yet. So we can take this and kind of see if I wrote a min function. I have this min whatever thing here, but that is not the min function. So if we look at diag pix, it's an int 16, and that's fine. We can't use an 8-bit integer because it's not enough room. But the next size up, U16, is a little bit more information than we need. So we're like, well, since it's way too many bits, why don't we just cut the bits in half and use a signed integer, and then we get the safety of a signed integer for free. That's the thought process behind that. So yeah, these are int 16s, and we saw that there's like a helper function section up here, right? And this is helper functions conversion. This isn't a conversion though. This is a this is not a conversion function. So we need to, let me divide that. So we need to go a little bit further up, and also let me kind of put section dividers here because there's a lot of different functions in here. So I just want a little dashed line to help me know that this section has more than one function. Okay, so here we have our helper functions, and we would just want to add another one, right? And it doesn't really matter if we put it on top or on bottom. I do like to put the newer stuff on the top when it's like when it's a section like this where there's no interdependency between these two functions. If there's no interdependency between the functions, I like to put the newer stuff on top so that it increases your likelihood of seeing it first. So this is actually an int 16 we need to use. And I see we don't have int 16 yet. So let's do define i16 and see if I finally have a shortcut that works for that. And I finally do, int 16. Well, yesterday we did not because we had written the shortcut code wrong and I had to fix that. Okay, so we have kind of the 32s are grouped together and the 32s are grouped together. And we can't group i's and u's together if we're gonna group by 32 and 16, but we can at least make these u's here touch each other, so I mean that's cool. Okay, so now int 16 AAC 2020 PAINT5D, and do we just want to call it min, or we want to call it like we should really call it like min and then i16 so we know what type it's supposed to be used with, because otherwise we could find ourselves in a world of hurt later when we use this with the wrong type. So let's call it min i16 to reduce the likelihood we're going to do something stupid, because we've done something stupid before many times actually, so let's try not to do it anymore. So let's say that this is, this is int 16 number 1, I16 int 16 number 2, right? We can be kind of heavy-handed with this and just be like, they're int 16s, do not forget about that, because if you forget about that, then you're just going to be in a world of hurt from my experience. So let's not forget about what their type is. Okay. And, oh yeah, PAINT5D min I16. Let's actually put like a comma in front of here. Format that properly. And min is a pretty simple, straightforward function, right? So we're just going to say, how about I16, how about we call it I16 min? Sure, why not, right? And we'll set that to some type of trap value where it's like, 554433, and that might be out of range for int 16. So let's do like 4433 maybe, because I think we get like a 32,000 roughly for an int 16. So I don't even want to be in the thousands unless I know exactly what that number is, which I don't right now. We also want to note that this is a trap value. And when I mean a trap value, we should have done this before, so let's take this. We can take this whole thing right here, trap value, and we can search our documentation and be like, did I denote what that was before? And I'm pretty sure I did. Yeah, trap value. A trap value is typically a bogus initialization value that is intentionally wrong / invalid. If we forget to overwrite the trap value before using the value, a fatal error is usually triggered. The idea here is to help us catch problems quickly by intentionally setting invalid state where we can. Essentially, we are setting traps for ourselves in the code to make the code more fail fast than it would otherwise be. Okay, so that's what I mean when I use a trap value. Okay, so going back here, we got our nice trap value, and then we're just going to say that, let's make absolutely sure, because we screwed this up before. You think you wouldn't be able to screw up a min function, but I have some flashbacks of screwing this up. So if I16.001 is less than or equal to, there's a good reason for why I'm using less than or equal to rather than less than, is less than I16.002, then I16 min equals I16.001, and then the same thing for the other one as well, right? So we're going to take I16, we're going to just flip this, right? So instead of 1, we could do, depends on how we want to do this. What makes more sense? Does it make more sense to flip this comparison operator? Or does it make more sense to just flip the variables? I do kind of like the idea of, it's easier to do it this way for sure. Well, no, because if we flip this here, we still have to change this. Alright, so I think the most symmetrical or analogous thing we could do is actually not flipping this, but just flipping all the variables. I think that's the most like when we're trying to think of the symmetry of the code and keeping things as analogous as possible, I think the best option is not to flip that sign, but just to flip everything else, right? Because then when we look at this, right, this is everything here is flipped, everything here is flipped, so everything's opposite land, right? Okay, so the reason why we use less than or equal to is because if we don't and they're completely equal to each other, then we never get an assignment, right? If this is our trap value, we're going to use a trap value. If we don't use less than or equal to here, we'll never get an assignment, and then we'll just have a bogus min value of like -433. We want that trap value to make sure that if we accidentally screw up, we can see it. And so if we did accidentally do this, that trap value would clue us in a little bit as we were debugging our code, but that doesn't mean we want to have a problem. This is just a safety measure here in case we screw this up, which you would think we wouldn't be able to screw up a min function, but believe me, I have done it before. I did it like last week, I believe, and it was giving me a whole bunch of trouble. So this min function looks good to me. the next thing we need to do is find where we're calling it, right? We have a place we're calling this, so, oh, and also, you know, we actually have to return it, right? If you don't return it, then that's completely pointless. And the compiler would yell at us, but, you know, let's actually... Okay, there. So let's look at where we're actually calling the min function. And it looks like it's only in that one spot. Yeah, so this min here... So in this section, what does this section look like? Well, this section still looks pretty nice, so let's not... There's a temptation to call this min something else, because I saw that other min I was searching for kind of put me into different sections, and I wasn't happy about it, but let's keep it like this, and then right here we're going to say define min, and we're going to take that function name, and this will be our 5th define, right? So we're going to have a little checksum right over here to keep track of how many defines do we have. Okay. So, armed with that min function, we can figure out the diagonal pixels location. So this diagonal pixels location is these guys right here. We also might want to say we might want to make a note here that when we're saying at diag pix x, we might want to make a note of that, right? That this thing is the same thing as this thing. When we're looking in code, if we see a comment that looks kind of like this, we're talking about this, right? So we might want to make that commentary. We're a little bit off, so let's see if we can kind of just go like this. Let's just go like that, so everything's kind of nicely aligned, because I have problems, okay? And then we'll do this, and then at diag px, diag py, and diag g. What the hell is that? That's not wrong. That's not correct at all. For some reason, that should be diag. Yeah, it should be that diag. Okay, cool. So we just made a mistake there. Okay, so after we get this min function between those two things, then we get this thing where we have the correct diagonal. So you'd be like, well, that's weird. Aren't these both diagonal? And well, no, they're kind of like this is like when we're trying to calculate those different diag picks. This is diag px right here, and then this is our next diag px is this thing right here. Right, and then our next one is right here. Oh, not that. Let's take this. Right, this thing. And then our next one is right there, right? And it just kind of starts collapsing in on itself, right? Right, all these are diag px, right? And you can see that, yeah, if the x value is over here, you could say, then maybe we're looking at this tile, right? Or this tile. But you know what? Maybe not, right? Like maybe when the x is over here, we're in here, but maybe the y is so far up that even though we're in here, the y is so far up that we're actually in here, right? So we have to look at both the y value of diag pix and the x, right? So when we are looking at this, let's take another one of these. Also notice that when we're looking at the data format, there's no mirroring here, right? It's the exact same data structure here, exact same data structure here, exact same data structure here and here. There's no mirroring, right? So these little quadrants aren't like mirrored in to be right adjacent to these data structures here, or these quadrants here, right? This is right here, and this is right here. This is not moved over here, right? There's no mirroring. So this block here is partitioned in the same way as this block, and that's actually very important. So the artist should be drawing something that's mirrored in towards itself. Like these graphics should be mirrored in towards itself visually to create a well-functioning auto tile set, but the data is not actually going to be partitioned that way. Okay, so now that I have that thing on my clipboard, or at least I think I do, but I was kind of ranting, we can make a note that we're talking about diag pix on the y, right? Diag pix on the y is the same kind of deal here, but it's so diag py, right? Diag py, did I got that right? Yeah, so diag py, right, is doing this, right? That's what we're doing for this is what we're doing for diag py, right? I don't know if maybe we should just do a little dot and do that. I don't know. It's in there, man. It's kind of I don't know. I don't know how we should point to that. I guess we could. I do not know. But you get the rough idea of what's going on. Let's not worry too much about the exactness of this. And we might want to make a note here that right, that diag pix equals the min of. We could actually do at symbol here equals the min of at diag pix. What? Boy, I cannot do this. This is not correct again. Diag p and then x. Okay, cool. So that's kind of what that stands for. Now, what are we doing? So, Glock pix to pain pix. So first of all, let's figure out, well, what is Glock pix and what is pain pix, right? So, in this diagram, I'm gonna guess Glock pix is the is our global pixel location, right? Like on this 512, 512. Where's the exact pixel? And then pain pix is probably all these guys. Yeah, pain pix is like all these things. So, so if we're looking at Glock pix is global coordinate of pixel. And we could do Glock pix means and just see. Do we have a definition for that? Yeah. Global coordinate of pixel, okay? And then pain pix means. And then we have pain pix, and we don't have to do the brackets like that. That's just for my shortcuts to let me know that I typed it correctly. Pain pix is paint pixels. And we can also be like, you know, we can also make a note here that when we're looking at the paint pixels, it equals all of these things. So I'm thinking that, you know, instead of redefining these in multiple places or making an index entry for all these, it may make sense to say that pain pix, or let's do this. Pain pix dot. Right, we could do something like that and say, well, conceptually. We could say struct conceptual. Well, so there really aren't, pain pix doesn't actually have these things, right? But if you wanted to think about it, then it'd be this, that, and that. So that looks kind of, this looks a little bit verbose for me, and I think it's kind of confusing me. So what I think I want to do is say like, make a little thing here. And just say, let's make a little diagram here and be like, you know, these are the conceptual members. Conceptual members. Members of PAINT5D, right? And then what we can do is that other more verbose kind of thing here. We could kind of throw it down here, right? We could throw it down here. Nope, throw it up. Yeah, there we go. And this kind of lines up. Yeah, it still lines up nicely. And we can just put that, you know, over here for reference, kind of tucked away there. Or if you want to see it, hey, it's over here. But it's not visually cluttering our index thing, right? And this is just so if someone wants to do painpix.this, they're going to be able to find this in the documentation somewhere. It doesn't actually exist anywhere, but if somebody wants to, thinks that it may exist because I'm saying that these are the things that exist in PAINPix, I want them to be able to find it, right? Till qua, I guess we should do till qua. We should do all of these. So 1, 2, 3, 4, 5, 6, or was it 5 or was it 6? See, I don't even know. Okay. So other thing I might want to do is we might actually want to make like a little checksum. We might actually want to be like just be like 1, 2, 3, 4, 5. Right? There's 5 members. Right? This doesn't have to be. Oh wait, but then we screwed this. How do we? So if we want to do that, can we do it like that? No. Nope, that's still not enough room. It does look kind of nice doing it that way. How about we just do this? They're members, and they are conceptual members, but we'll leave that as an exercise to the reader to figure that out, right? So Paint Pixels does not actually have these things as actual members. It's a conceptual object, right? We're not gonna. I get how we might want to kind of do that. Actually, that might make sense. I mean, because this is kind of a big thing where we got a lot of things going around. It is kind of like begging for an object here. Alright, with all this stuff. But I don't know if... I don't want to add more surface area to the code and nest things even more. I like the flat structure, even though this is a pretty beefy function here. So that is kind of like, maybe not, right? Okay, so till qua means. What does till qua mean? Do we have a definition? No, we don't have a definition. So let's find this. Offset subtile quadrant index. Okay, so so it's offset it's an offset tile subquadrant index. And so tile, the till, is coming from here, and then the A, so offset. I want to think about where the qua is coming from. It's coming from here. Till qua. Quadrant index, right? Till qua. So offset tile. Offset tile subquadrant index. So what that is if we're looking at here, I believe it means this guy, this guy, this guy, or this guy, if I'm correct. If I remember this correctly. So we could look at the math here and kind of be like, well, is that the math? Or have we even finished the math for that? So we can see that we're kind of abstracting something as a 2x2 tile map. So there's 2x2s in different areas, so that doesn't necessarily mean that's what it is. But we also see multiplication by 256, so that's definitely what it is, right? So when we're looking at these diagrams, we can say that since we have the diagram here and there's a whole bunch of empty space, we might as well kind of like make note of that, right? So we'll say like right over here, we can say that at til qua and til qua right here equals 2. I want to make that a triple equals just because that's the way I've been writing it in the diagram, even though triple equals doesn't even exist in C, and I think that I'm doing JavaScript again, right? So let's take that and kind of roll with it and just be like at til qua equals 3, right? So that's when we see these numbers right in here, that's what those are. And we could do this again and indent that correctly. And the same thing over here, right? We could do this over here. Let's just take it from here, and we know we got to go from up here to here about. Yeah, there we go. And the til qua equals 1, right? And then over here it equals 0, but do we have enough room here? Well, we kind of have enough room, right? So at til qua equals 0 here, right? Alright, so we just want a way to kind of grab on to what's going on here. We want to be able to, when we're looking at the code, and it seems I've screwed up more. When we're looking at this code, we just want to be like, oh, nice diagram, bro. What does all this stuff mean? So here's til qua, here's tile A, right? And you might also want to do like at tile A like this, because we just want to be able to say, hey, there's little at symbols here. This is actually a variable, right? Same thing with at tile exponent, right? The tile exponents. And I'm saying that when we're looking at this diagram, I want the at symbols to be like, hey, look at this. This variable actually exists somewhere in the code, right? Okay. So now that we know that, that's good. So tile qua, we kind of figured the mystery of that out. Now I see we put a little 3 here. And the thing here is, let's get rid of these numbers in the middle, because it's making it look like it's that actual point right in there, but it's not. This quadrant, this tile qua thing kind of represents the whole thing, and it does not represent that very specific point there, so I don't think we should have those numbers there. That's actually very confusing. Right, because diag fixes that thing in the middle, right? Or, well, it's not always in the middle, but you kind of see. So let's remove this 3 here. And what else do we need? Well, let's just kind of keep on filling this out. So tile exponent. So what is tile exponent? We've already done tile exponent right here, so we don't need to re-diagram that. We'll just say til exp and then means, and we should have a variable definition for that. So tile exponent. So tile exponent, right? And the we could do that like this. So TIL tile exponent. Tile exponent span in pixels equals 2 to the power of tile exponent, right? So when we're trying to figure out, well, how big are you? This is how big it is. Well, kind of. This is really a relative span in pixels. It's not necessarily its absolute size. Right, so really this is like a relative span in pixels. But I guess we could just call it span in pixels just because it's, I don't know. Sure, let's just keep that there. It's better than nothing, even though maybe it's not exactly what we want. So, tile layer. So, till lay means, and we should have a, till lay means, right? So, do we not have this? How about till lay means? How about that? Do we have that? Nope. So, I'm going to guess we don't have this either. Till lay and then means. We probably don't have this at all either. Okay, so we need to take this and make a little definition in our shortcut. So now I believe that is just tile layer. That's what that is. But let's just make sure that we have. How much of it do I need to put in my documentation? Do I have a? If I type till lay, do I actually get that? Okay, no. So we got a lot of stuff to do here. Okay, so we're gonna take our shortcuts here, and we're gonna over here we're going to just make notes for this as well. So till lay, if you do till lay like this, we just want it to say, oh hey, you're right, good, that's exactly what we wanted. It's exactly spelt correctly. That's a thing, it exists, you know? Okay. And if we do till lay like this, or till lay, then it's just gonna correct the spelling, right? And if we do something like lay till, or lay till, or lay till, then it's going to say backwards, use till lay. And then eventually, you know, these things that are backwards might end up eventually one day meaning something different. But until then, we're going to correct you, say, hey, you typed that backwards. Here is the forward version. Okay, so next thing is these means definitions here. Obviously, means could be like an average or whatever, but not in our shortcuts. We've kind of, we used to say this means, define this, definition. We used to use a lot of different other words for this, but we've kind of settled on using means when we're like, what does this mean, right? So, till lay. Till lay is, should be like tile layer, and it should be an index 0, 1, or 2. 3 layers. Right, so there should be 3 layers when we're talking about tile layers. That could change in the future, but right now, looking at the data and looking at how we're kind of deciding on doing that, it's 3 layers. So, with that, we're going to take this tile layer here. We already made like a nice definition, so we're just going to copy it from our shortcuts and also put it in this nice little index here, right? And this is us kind of like gaining our bearings, right? We drank a lot of coffee yesterday. We were all over the place, and now we have to kind of like figure out, oh, where were we when we did this last, and collect our get back into the headspace, right? So as we're getting back into the headspace, rather than kind of waste time getting back in the headspace, it could benefit from just kind of like writing some code comments so that other people kind of can find this, right? So alloctx means, right? Okay, so that looks like we do not have a definition for that either. We were making a lot of definitions kind of on the fly last night. We were like all over the place, and you know, it made sense because it's like we wanted to make sure that we were as formal as possible, where it's like if we have this variable name somewhere, we want it to have a name. We want our variables to have very strict names, very strict definitions. And sometimes, as we're making formulas, the names kind of explode. We're like, oh god, we start to juggle a whole bunch of very new variables that we've never used before, and then we have this kind of like administrative effort we have to undertake to like record all of them, right? So the local tx is local. And is tx a tile coordinate, or is that just a tx because it's, you know, it's just a t for some odd reason, or does that actually mean tile x? So if we look at some of this stuff here, so local tx, local tile x coordinate, that's good enough for me. And did we put it in here? Do we have a loc tx as like something in here? And we do not. So I know what local tx is. We should kind of diagram that. So we have this diagram here, and what we could do is we could kind of like make this into a whole bunch of cells or something, or here's what we're gonna do. We're not gonna do that. We're gonna say we're gonna take this thing here, and we're gonna cut and paste and say that this right here that we are looking at is, it's probably a better way to do this that isn't so ugly. Like maybe we could do it like this and kind of say that, you know, when we're looking at this right here, this right here is going to be this thing here, and this right here is 0, 1, and 2. So the layer at tilde equals 2, or 0, 1, 2. Yeah, tilde equals 2. So let's put that in the center. Why not? So at tilde equals 2, and then we can do that over here, right? So at tilde equals 0, and at tilde equals 1. So when we're looking at this, what does tilde mean, right? And we can see it in a diagram here, because it's not up in here, is it? Oh, it is up in here as well. But now we have it here. And, ooh, is that correct? Oh, yeah, that's correct. Okay, yeah. So when we're looking at one of these things, in here, right here, let's actually take the sizes here. So the size of here should be 256 by 256, I believe. And the size over here is different, right? Because we're zoomed in. So let's look at that. That should be, yeah. So 512, and our partitions are 256 by 256. So what we can do here is we can say, let's kind of put a little plus here so I can see. I want to just see where the center of that is. Okay, cool. So this is 256. And then analogously, we can take this exact same thing and we can put it down here. And we can say that this right here is 128, right? Now, when we're looking at something else, like over here, it would be a different size. So let's say at tilde equals 0, at til x, so the tile exponent equals 0. And yeah, so when we're identifying this, that's the values we're going to use, and the diagonal for this is 0. So when we're looking at the diagonal, at diagpix equals 0, right? So diagpix. Alright, so here's our different diagpixes. And so the diagpix for the tile exponent when 0 is 0. What else? We also want to, we might as well just kind of throw this in more of the center. Make that look a little bit better. And right now we have all this division and stuff here. I don't know if that matters, but this is 128, correct? Yeah? 128, yeah, this is a 128 region. Okay, yeah. And we could say in here, we could kind of like divide these into kind of cells here and try to kind of think of it as a bunch of pixels visually when we're looking at this diagram, which is not going to work perfectly, but we could do that, and that way visually when we're looking at it we can think of it as something different than the other kind of cells that we're looking at, the other ASCII diagrams we're looking at. Because right now, you know, all of our diagrams are just these boxes. How do we kind of tell the difference between them, right? And so it might make sense to remove the patterning on the sides so that this looks like a kind of a different thing, like visually. Might not work totally, but yeah, like when we're looking at this, and then I believe if we use some underscores, we can kind of make like some cells, you know, not to scale. Or maybe we just want to use minuses. That kind of works. It's not the best, but the idea is that we want to think of this as like pixels. Alright, just tediously kind of making some diagrams to get our bearings, to remember what we were doing, you know. Okay. So, you know, we might want to make a note that, you know, this is not to scale. And also, no, backslashes or forward slashes give us problems when we draw diagrams. So, let's go, like, here. Let's go into here, into this last cell here, and say, you know, loc tx equals 127. And loc ty equals 127, and just make a note that it's not to scale. Right, so we could say local pixels, and then, oh god, we could say, let's go up here a bit further and say local pixels, and make a note that this is not to scale. This diagram here, right, we can't fit 128 pixels in here. So when we're looking at this conceptually, we don't want to get confused and be like, that's not the 120, oh, and these are both the same number, right? And we might want to say that, you know, 128 minus 1, just so that you conceptually can understand there's like this off by 1 error thing going on here. And you can see the relationship between the width and the coordinate a little bit better, you know? Yeah. So now we have the local tx, local ty. And I don't think we had that anywhere else in our diagrams, did we? So let's just double click on these guys and see if anything else lights up. No, so nothing else lights up. So this just helps us. We're trying to be like, well, what is loc tx, what is loc ty? And hopefully you can kind of see that these arrows are kind of pointing to this thing here. Now maybe it might actually make more sense to go like this, like that, you know? Like maybe that looks better, I don't know. Yeah, I don't know, man. Right, angled lines don't really work well in ASCII, so I think that's the way we're going to go with our diagrams here. Okay, so now that we have this diagram, have we said what loc tx means and loc ty? No, we have not. We see that we have a local tile x coordinate, and bx is for brush x. So we might also want to say that, you know, bx stands for brush x coordinate. Okay, and then by is brush y coordinate. they local chords. So the brush X and brush Y coordinate, I think we're gonna make those local coordinates. So it's actually loc TX and loc TY are kind of synonymous for the brush X and brush Y. So I don't know if I have a BX means. BX is pretty vague. BX means. But sure, why not use, since BX, sure, why not, well, let's take these definitions as well and throw them in here as well. And the local TX, local TY, we're going to throw that in here as well. Okay, so in my shortcuts file, we're going to keep on adding to it, right? So BX and whatnot. So let's do, you know, BX means, and BX means, and B dash X means, and that should be good. Actually, one more. B underscore X underscore means like that. And then if you type it, we actually want to know that you typed BX and not something else. So you want to put some square braces around that. And we want to do the same exact thing for the Y. So why not just paste this here and then replace the X's with the Y's, right? Because that's really all it is. Okay, and then brush Y coordinate. And then if you type like a BX or a BX like this, then we'll do this, right? And because it's such a shorthanded thing, there's the possibility that eventually I may be, you know, using it somewhere else. I might need to find these in my shortcuts. And sometimes searching for very small tokens in a shortcut, in this gigantic shortcut file, can be kind of hard. So I'm going to put square braces around this one, just so that I can find it in the future a little bit easier. So BY and B-Y, same thing, BY, and then B-Y like this, just so I can find them later if there's some type of collision with my shortcuts. Looks like I'm going to keep on pairing these together, even though that's not the way I usually do it. So BY, if we type BY like that, we got it correctly, correct, right? So we're just going to do like this and do bonds hexa, right? Just a little check mark to be like, yep, that's the thing that exists, right? And then BX, same thing. So BX and U plus bonds hexa. And it's a little tedious to do all this, but I think it pays off to know exactly what our variables mean, to have very strict definitions as to what our variables mean. So loc TX, I don't believe, was a thing in my shortcuts. I mean, we looked around for a bit. We have it referenced in some places, right? But we actually have not defined it anywhere. So we're gonna take loc TX and do the same thing. You know, if you type it this way, here you go. That is correct. Thank you for typing it. You know, and I guess since we're keeping this pattern, we might as well do the TY now, right? If you do TY, local TY, same thing. And we could probably just auto-generate this a little bit faster, but it also gets it into my memory. That's my excuse. So loc TX or loc TX or loc TX or what else? Loc TX or loc dash TX, like that. Any of these combinations, we want to see a correction of loc TX. Right, so there's very particular spacing that we're using to make everything either a grouping of 3s or 7s. Okay, so same thing with loc TY, loc TY, loc TY, loc TY, and loc TY. Okay, gonna do loc TY, baseline. What else do we have here? We need the actual definitions. So loc TX means, loc TX means, loc TX means, and how about loc TX means? Is there anything else we're kind of missing? I mean, there's other combinations we're missing, but is that good enough? Are we satisfied with that? I think I'm satisfied with that. Loc TX means local tile coordinate x. Okay, and then the same thing for the y's, right? So we'll take this, we'll copy it, and we'll paste it, and now we got the definitions for the y's. Well, not yet. We obviously have to replace this, right? So anything where we see those x's, we're just going to replace it with y's. Right, and yeah, so loc ty. Cool. So we have the definitions for the x's and y's for the locals, and also for those brush coordinates. They're also defined in our shortcuts. So if we want to reference them next time, we'll know. And the idea is that, you know, if we use them in our code again, we might want a quick refresher on what they mean. It might have been a while, right? And we can see, we can actually take this here, and we could paste this here. Usually a bx value, and that's probably true in this system in PAINT5D, so we can do that. Remember, these definitions are going to be specific to PAINT5D. So if you know, if the definition kind of varies in different places and different systems, it doesn't matter. These definitions are going to be specific to PAINT5D. And if local tx and local ty mean, you know, I don't know, let's see, I don't know. Let's say that local tx in another file means local tangerine x, and local ty means local tangerine y, like in another system. That's fine, because it is kind of a vague definition here. But we can say that within this file, we know that it means exactly this, right? So we can be a little bit more specific than we would otherwise be because of where we are in here. So we've kind of defined all those things. Cool. And now that we've made this here, we still have to finish this formula, right? We've kind of gone over what some things are. Now this remi is like for a remainder. And the idea is you're going to take the values, the coordinate value, the global coordinate value, and we're going to whittle it down. So if we can see this, the PAINT5D Glock pix to pane pix, right? So the Glock pix is the global pixels, and we're going to whittle it down to get all these different values, right? We're going to whittle down the remainder until eventually we'll get the local tx and local ty, and have these other integers that identify where it is, right? Because it's local, so we need a context for the local, right? Because it's a local coordinate, but like which cell block is it in? And then, well, which size cell block it is in, and then which layers it is in, and all those other things. So the local just tells us a local pixel within one of these partitions, but doesn't tell us any of other locating information, right? So we need these other pieces of information right here to kind of figure that out. Okay. So with that, let's go back to our definitions here, because there's still some more things that we need to know about. So for example, the remainder thing here, and also this temporary, right? So this is a temporary integer, right? That's what that is. So let's make a note of that. So I'm going to take a wild guess and say that I don't have definitions for these yet. So let's do that. So tempi x, temporary integer x, probably usually a coordinate. Okay. Tempi y is going to be temporary integer y, usually, right, is usually a coordinate that we're whittling down. So we might as well make a note that, you know, usually that's a coordinate. When we're talking about tempi x and tempi y, but I mean, we have x and y, so that kind of implies a coordinate. Actually, it does not. It could be like a cell location, but a cell location is kind of a coordinate as well. So here we're going to change that pixel coordinate. It's the location of a pixel, right? Not always. Well, yeah, It kind of is. Pixel starts as, I don't know. Whittling pixel coordinate. I say whittling pixel coordinate, and that's like, what the heck do I mean by that? So we might as well do like, we might want to say, what do we mean by that? Because I don't think that is going to make much sense. But basically I mean that I'm whittling down a coordinate value and extracting different pieces of information from it. So let's make a note here and just describe what I mean by that. It means I'm taking a large coordinate value and whittling it down over successive calculations until nothing is left to derive various local coordinates that the original global coordinate represents. In other words, we whittle down a global input coordinate to get all of the local information, all the local variables that together can identify that global coordinate. And then we'll just say like C, and then there's a specific function that we're actually doing that in. Therefore, we might want to make note of it. So we got this temporary thing here, and oh, you know what? This is not a whittling thing. This is what is this? I don't even know what it is. I think we might have been doing like we might have made this, and then we were like, oh, we're gonna call it Remy for remainder, whatever, because that's better. So we're gonna take temporary x and temporary y. We're gonna comment this out because I don't know if we're ever gonna use it because we're using the remainder, and that could have been just a thing. And then the whittling coordinate thing, that's still valid. It's just so C Remy x, or what is it called? I call it Remy underscore x, maybe? Rem ix, got it. So Rem ix and Rem iy in we could make a note of the function, right? So we could say, you know, see this thing, the function is this, and then the file is this thing here, right? And then we could also do, you know, at vid iid, and it is 2020, oh, not that, it's 0068, and the time is 1 hour, 18 minutes, and 43 seconds, okay? So to describe at whittling pixel coordinate, what I mean by a whittling pixel coordinate is a coordinate that starts off basically as a global variable, and we do calculations to it in a loop or iteratively over and over and over again, and just chop off more values off of it until it ends up 0, right? And we're just extracting different pieces of information from it. And so if we go over here, right, like we could have a global pixel in this 512 by 512, and we got to figure out like where is this global pixel. So the first thing we could do is we could chop off a 128 section from it, right? We could chop off a big 120, or sorry, we could chop off a 256 section from this pixel coordinate, right? So we could chop off, subtract 256 from the x and y to figure out, hold on, let me say that again. So you have this global coordinate right here, and we have to chop off things from it in order to figure out the different local coordinates that compose this. So the first local coordinate that composes this point here is the fact that we are in this third cell here, right? This 1, 2, 3, 4. The third cell being tile quad 3, right? So we're in tile quad 3. We know that the quad x and y location for this is 0, 1, and also 0, 1 here. So it's 1, 1 is the xy equivalent of the index 3 here. And since we know that, we'll take 1 times 256, and that gives us 256. So we'll subtract 256 from both the x and y of like this test coordinate right here, right? And then once we've done that, we've extracted a piece of local information, being the tile quad. And now we have a new global coordinate, right, that's just local to here. And we need to do another operation where we kind of whittle down again, right? So the next thing we need to whittle down is, well, are we in this cell here, this cell here, are we in this cell here, or are we in one of these cells, right? So in order to do that, we have to, figure out what diagonal we're in, right? Are we in? Is this the origin of our diagonal? Is this the diagonal origin? And if so, then these are our cells. If this is our diagonal origin here, then these are the cells we're looking at. And then if this is our diagonal origin here, then it's these cells we're looking at, etc. and etc. So since this point is in this first cell here, then we don't actually. I don't think we do we subtract anything. Well, if we're in here, yeah, we don't subtract anything, I don't think, because the coordinate is already local to this space. But perhaps the global coordinate was right here, right? Then we would have to subtract only on the x, 128, to take this and zero it out and shift it over here, right? So when I say whittling, it just means I'm taking a global coordinate and I'm shaving numbers off of it until I can extract all of the local information, right? Okay, so going back to the definitions we're writing, right? We haven't done anything for the remainder variables, right? You got this temp here, but rem ix and then rem iy. Okay. So it just means remainder x, remainder y. Pretty simple. Remainder integer x. Right, there's a reason why there's that I in there. Remainder integer y. Okay. Now that we have that, we don't have those definitions in our shortcuts, so we should also put them here. So this is just going to be a very tedious process of kind of like taking all this stuff and being like, let's document it, right? So these things here, they don't exist in our shortcut file yet. So if we go over here to our shortcuts, let's just make sure before we kind of enter this stuff. Yeah, I don't see it here. Let's take this thing here. What about this thing that kind of spells remix? Nope, not at all either. So we'll take this, and what we can do is we can say this is already a pretty good thing for like a definition here. So why not just say like let's just take this. Right, we want to verify that it was spelled correctly. And then we'll say like temp tempi x. Oh, I see. Don't we want to do like oh, I see. Okay, no, it's that P in there. Okay, I was just making sure I was being consistent. Tempi x means, and temp x means. Do we have that? Oh, we have a like an older variable where we do that. Or do we? So let's take this for a second. I think that's like an older variable convention we used. No, I don't see it. Let's go with it. Let's just do temp x means. I don't think I do have something like that. So temp x means, and then, you know, that's my thing, right? Tempi x, tempi x. We don't have tempi x means like that, do we? Okay, so let's do that. And we'll do the same thing for the y. So we'll take this and we'll say, oh, tempi y. Okay. And for the remainder, rem ix means, or rem ix means, or rem ix means, let's just make sure that's not a thing, right? Because I'm spelling out remix, so there's the potential. And then rem remix means. Okay, so that's good enough for that. And then we'll also take this, we'll paste it over here, and we'll do the same thing for the y, right? So we have these definitions in our shortcuts at our fingertips next time. Or if we ever ever use these variables, we know kind of what it means, right? Okay. Now also, what about typing them? So we could probably do this in a batch, right? So the only thing that is different, well, we got to do it in a batch of the temp and then the well, actually, no, here's what we could do. We could do, no, we can't really do it like that. So tempi x, and if we do tempi x, we're going to do tempi x like that, and then like a little bonds hexa. Oh, hold on. U plus bonds hexa. So how can we do this? I think if we take tempi x, we can convert that to a y version. Or could, okay, you know what? Let's just do everything for tempi x, and then let's kind of duplicate everything in a smart way so that we don't have to keep on doing this kind of tedium thing here going on here. So, so if we do tempi x like this, or temp, oh, but we've kind of, let me think about it. So tempi x means, or oh, sorry, temp x, or sure, why not? And then for this, we're just gonna say tempi x, right? We're just gonna fix it, right? And then if they do x tempi, or x temp, I don't know, or x tempi, then we're gonna just correct them to be like backwards use tempi x. Okay, so with this, I think what we could do, I know the first thing that's obvious is we can take what we've just written and do a y version of it really quick, right? We can search for the x's and we can replace it with y, right? Simple deal, right? Now for the converting it to like rem I think we could do this as well. We could take this, and if we take this as the source and we replace tempi with rem I like that, right? So same amount of letters, right, like this. Then I think that will get us, we might get something kind of weird for some things. But let's try to duplicate that and see if that kind of suits our needs, or if auto-generating it like that kind of resulted in kind of like weird things, right? Like maybe it doesn't look exactly, maybe it's not exactly what we expected. So rem IY, that is rem IX, that's how we expect it. Now the improperly spelled things are kind of weird, like rem E-Y, rem, right? So we might want to make some more entries here. So rem IY, like we don't have that, do we? Right, and rem IY like that, or like rem dash IY. Oh, this is a thing right here. This dash IY I do not think is a thing, right? Okay, So these two other options are not in the misspelling. So let's paste them here, and then let's do the, well, remix is a thing, so hold on, remix. Like, I might have got, like, overclock remix, so that's why I was kind of worried. That looks good to me. We might want to say, like, Y, Remy. Y Remy. And then we want to call this one, like, X Remy. Or X Remy, like that, or X Remy. So Y Remy like this, Y Remy, and Y Remy, right? Okay, so that's pretty good. Alright, and that's, once again, an explosion of variable names, right? It's like, that's a little bit crazy, but that's the way we do it. So let's put this over here and see, well, what other things do we have to do here? We got tile quad, right? We got all these things. So this is, well, tile quad is already done. Tile exponent, tile layer, local TX. So this I16 GTX, it looks like we're taking global TX and just making it, making a int16 version of it. And we're just trying to keep it the same size and characters. That's what that is. So let's take glow TX and say, you know, this is basically a global tile X, and we should have, like, yeah, global tile X coordinate. That definition works for me. So let's take that, paste it here. Glow TY, same thing, is a global tile Y coord, and let's remove that extra space. And let's take the GTX thing as well. So let's take I16 GTX. So signed 16-bit integer version of glow TX. That's what that is, right? And the Y version is the same deal. It's just a signed 16-bit version of glow TY. What else is missing here? So OX qua, whatever the heck that is. That's like some type of offset to quadrant. And I see 256, right? So because I see that 256 in the multiplier, I can go to my diagram and I can see, oh, there's a 256. So we're talking about the offset to from here to here or to here, right? That's what that is. Okay, so it's offset to the appropriate tile claw, right? So we're looking at OX qua, offset in pixels to to correct til qua, right? So we're taking it to that tile quadrant. Or is it the offset in pixels? No, because we're multiplying it here, right? So it's not the offset in pixels. That's if you multiply it by 256. This is the cell /partition X location of til qua, right? So til qua is the index, and this is the x coordinate of that index, right? And so OY is the same deal for the OY, right? So let's take that and make a definition there as well. So the idea of meticulously doing this is, yes, it is a pain, but for somebody who is gonna, somebody new looking at this code base is going to be thanking us that we kind of meticulously took the time to say, here's what all of these things mean. Or, well, I hope they will. Maybe they'll just be ungrateful people. Ungrateful people to, ungrateful people who were born to unwed children, right? Maybe they will be that, but, hopefully they'll be grateful. Okay, so we have these three things that we still need definitions for. So let's do that. So let's add these definitions here. And I really need to make a way to automate this kind of a thing. But whatever, let's just throw it in. Let's just throw it into... I'm going to take those three things, I'm going to paste them into my shortcuts, and then we're going to meticulously kind of make notes for that as well. So let's make sure that these don't exist anywhere yet. So it does not look like we've defined it. We've defined the Glock picks there, but we haven't defined this. Now this definitely doesn't exist anywhere, but we want to double check. Notice that I'm only checking the X's, because where there's X's, there's Y's usually, and so if I've been good about how I've been doing that kind of a thing, I shouldn't have to worry too much. Now, I like this as taking this as kind of a list of things, because a lot of this is going to be very redundant, right? So we could probably do something like this. We could take this and make a list and try to do one entry for all of this stuff and have everything duplicated, right? So if you type it correctly, then we want to just do this, right? Okay. And if you do... Oh, the problem is that with this, we can't get too far with that, can we? So let's just do Fark template and do what we can do with what we've made, right? So we can take this thing, we can do this, we can paste that there. We can take all of our find and replace options and we can put them here. We're gonna find this TX thing, right? And then let's do that and go Fark. And now we have all of the things that are gonna spell correct what we have typed, right? So all the correct spellings. Or not spell correct, but if we type them correctly, it's just gonna say, yep, you did a good job. And that'll be that. For the other things where we type things kind of incorrectly and it needs to be corrected, we have to think about... So fortunately for us, it looks like we only have X and Y in the variable names, right? And since we only have X and Y in these particular locations, we can do a naive find and replace to auto-generate everything we need. So glow TX and glow TX and glow TX like that, or glow what else? Glow dash TX like that. Yeah, okay. So if you type that, we'll just do glow TX, right? Well, we'll fix it for you, right? Now, if you do something backwards like TX global, or TX glow, or TX global like that, or TX glow, or glow, or TX glow, or TX glow. If you do anything like that, we're just going to say backwards, use glow TX, like that. So the proper version. Glow TX. Okay. The other thing was, well, what does this mean? And we have the definitions down here. We should probably tackle those all alone, since, yeah, let's not kind of batch those. Let's do those individually down here, the definitions. But yeah, so we have the spelling and then the misspellings. And let's take these, make another template, and we'll take the source, we'll take the keys down here that we're going to look for, or the replacement keys, and the key we're going to look for is the first thing, the TX, and we'll take that and we'll just run that. So if we run this, we now have a whole bunch of stuff. Is it indented? Sure, that's good. The indentation I think is good enough. We might want to separate it a little bit like that to make note that we're looking at different things, that these are kind of slightly different things. It's a related section in our shortcut, so as we are partitioning this out, we might want to make note of that. And because I'm OCD, let's try to make this partition line kind of symmetrical. Sure, that works. And using this partition line, we can kind of put it where it needs to be and say, does this glow TX make sense? That does, but it looks like we have two of... Oh no, we screwed this up. We took all the time to make that nice line, and we did this completely wrong. Totally wrong. So that's what we get for trying to batch this out. We actually have to... Yeah, we can't do this. We can't auto... This is why I just, instead of doing this, it's like, let's not try to save time. Every time I try to save time, I end up spending more time trying to find a shortcut. Okay, let's just do this manually. Right, so we have the global TX values, and now we just need TY values, right? So we're just going to have to spend the time to do this, because by the time we figure out the most efficient way to do it, we could have already done it the simple, stupid way, which I have noticed is a very common thing in life. It's not just common here. It's common with a lot of things. Now, if you find yourself doing something repetitively all the time, like this, finding a better way, like I could make definitely a better shortcut script for this, but I haven't, so oh well. So we'll just whittle this off, and we'll kind of do the same thing for these things here. And so what I've noticed, yeah, we just gotta do this. Yeah, so let's do like if we do int16 GTX, or int16 GTX, or int16 GTX for some reason, or int16, and we can get less regular when we do it this way as well. I16 I don't care too much. Okay, so yeah, if we do that, right, we're gonna do this, right? We're gonna have a correction, and we can do the same kind of thing with the we have the backwards here. Okay, and the same thing, we can do corrections for the y's as well. So anywhere we see these x's, we're gonna replace them with the y's. Okay. And then we want to think about, well, what about backwards? So int16, so if we do GTX I16, we want to say that's backwards. GTX I16. GTX I16. Alright, so all those forms, and then, I don't know, GTX I16, or GTX 16, right? Or GTX 16, or GTX 16, like that. Any of these, I'm going to just say that they're backwards, and use I16 GTX. Then we can take the GTX, paste that, make it a Y, right? So then we can have all the corrections for the GTY variable, right? So a lot of this is very redundant, but the idea is for me to go slow and steady to get where I need to be. Okay, so let's take that. And now the last thing, we gotta do all this kind of code again for the offset X, and then we need the definitions for this as well. And then we'll make this like a new section in our shortcuts. So if we do OX qua, then that's correct. And did we already do the correct versions? Did we do like a big chunk of correct things at the beginning? Yeah, we already did a big chunk of all the correct versions, so we don't have to do that. We just gotta go OX qua, OX qua, qua, OX qua, or OX qua, OX qua. What's another thing we could do? We could do like this, OX, and then qua like that. And if you do any of those variations, we'll do OX qua like that. Now, really, I don't know why I did... oh, it's offset X, and then the specific aspect is quadrant. Right, general to specific, so that does make sense that I did it that way, because it's general to specific. I just want to make sure that made sense. So if we do qua OX, or qua OX, or qua qua-ox, or qua-ox, like that, or qua-o-x. Or, I don't know, there's probably one more combination I could do, like this. Oh, we could do all dashes. We could do qua-ox like that, yeah. If you do that, we're going to say backwards, use ox, and then qua, and it's general to specific, right? We want to make a note that that's general to specific. That's why we do it in that order. I have not been consistent about that correction, but yeah, anytime we're ordering something and there's a specific order to something, anytime there's a specific, what am I trying to say here? My variables usually have a reason for the order I put the different, when I glue terms together, and I glue the terms together to make a variable, the terms are usually ordered in some type of general to specific way, unless there's some other thing in my way that's grandfathering in the other ordering. But most of the time, it's going to be general to specific, and there are like a few exceptions. Just like any natural language, there's exceptions, right? Okay. So now, we've made all the different entries for all the variables in our index up to this point. And I believe there's even more still, but we're getting there. So we have a nice little index here. We got them in our shortcuts. What about these diagonal pixels? Do we do diagonal pixels X and whatever? Are they in our shortcuts? Are they in the file? So I don't see it here. What about here? If I do it here? So we have it in the diagram. Definitely, it's in the diagram. But it is not in here, which I'm actually kind of surprised, because I guess we put it in the diagram and then we kind of forgot about it. So diagpix. I might want to say, I don't know where we're going to put it. Well, let's just put it by where it's used in this code, right? If we see it here in the code, we might as well put it near where it's being referenced, I guess. So diagpix, so this is, diagonal, pixel, chord, X, and it locates the origin of one of these tile lay cells, right? Or does it? Yes, it locates the origin of the array of tile lay cells. And we don't have much room, so origin of tile lay. There's technically 3 of them, so we could do that. That's kind of weird, but better than nothing, right? We want to summarize this all in one line. So if we don't have, so we can't be too verbose about it, right? So origin of tile lay, and there's 3 of them, right? For any given size, there's 3 of them. So I like that. Diagpix, I believe, is up here, right? Diagpix is already up there. Yeah, so let's just do the entry for this in our shortcuts. And once we've done that, I think we've kind of documented everything, and we'll kind of reload our shortcuts and maybe take a break, right? Like, we'll start reloading our shortcuts, and then once the shortcuts are in a stable state to where I don't have any variable collisions, or I'm fairly certain that there aren't, because it takes 5 minutes to reload, but the mistakes usually pop up right away because I put the new shortcuts near the top of the file, so that when I run my sorting algorithm will most likely encounter duplicates early on rather than later on, just because it takes 5 minutes to sort all the data. Okay, so diagpx, like that. Let's make sure this isn't anywhere else in this thing, because I might have made a mistake. Okay, so yeah, so when we type this, we just want to make say diagpx, and say, yeah, you did a great job. You did it correctly, right? Now, because the only difference between these 2 variables is x and y, we can do everything for the x, and then we can clone it for the y. So diag p dash x, or diag px, or diag px like that, or diag dash p dash x like that. Or we got all underscores, we got all dashes, diag p dash x. How about diag p underscore x like that? Yeah. Okay, so those are all good options for misspellings that are close enough that we're not going to say you did it wrong. We're just gonna give you the correct thing, right? And then other misspellings where you do it backwards, we're going to be more obnoxious about it, right? So if we do px diag, or px diag, or px diag, we're going to say you did it backwards. Px diag, or how about all dashes? Yeah, px diag. Now we don't have that yet, so if you do that, we're going to say backwards, use diag px. Like I said, now, because everything is so similar here, we can take all of this and we can clone it. So we're going to do this, and then we're going to do farc template. And really, we could just put this in a new file if we wanted to. Right, because this is just a very convoluted way to do find and replace, which works better. For like large things, because we only have one replace key here. So it's like, why do all that work when we only have... Ooh, you know what though? We're looking for x and replacing with y. My bad. Otherwise that would not quite work. Okay, so run this. And now we have the y version of the variable and all of the misspellings for that as well. Then we can say, right here, we can say diag px means, diag px means, diag px means, and what else? Diag dash px means. Good enough for me. Good enough. That's enough definitions, I think. Okay. And then we can put this here and here. And we're going to take what we've already written and we're going to paste it down here, and then we're going to, change the x's to y's. So yeah, just a lot of very redundant stuff. And hopefully, eventually I will get to somewhere where okay, good enough. Let's take that. And this is like a new section in our shortcuts. These are just comments, right? Because like we did all this cutting and pasting and replacing, and I just want to make a note that it's like a new section. It's just a rough way to get my bearings when I'm looking at this huge file, and I want to know that, oh, there's a line here and there's a line here. These must all be kind of categorized or related to each other in some way. Okay. So now, I think we finally have all the variables kind of written down here, and we're ready to kind of keep on doing our formulas here. Right, we have this little error here, hashtag error. How about Glock picks though? We had a thing called Glock picks. Glock picks, yeah, it's right there. Is that in here? Like we have pain picks, yeah, Glock picks, pain picks. We can say like Glock picks dot glow tx, and it's not really an actual thing, but Glock picks dot glow ty, and that's not how we spell them, is it? No, it's ty like that, and tx like this. And these are conceptual. I might want to say something like that. I think I already have an annotation for like @conceptual members, but let's just take this and see if when we do a case insensitive search for this, if that is in my hashtag documentation or if I want to make a note of that. So let's take conceptual members and say, nope, it's not in here. Let's say, what do we mean when we say conceptual members? @conceptual members means the variables can be seen as belonging to a conceptual struct or type, but there is no such formal struct or type in the code. For example, var first name equals John, var last name equals Madison. Right, so conceptually, these could belong to a full name struct. And first name so first name and last name are conceptual members of a full name struct that doesn't actually exist. In other words, a conceptual member is a member of an implied object. Right? So that's what we mean when we say conceptual members. Let's just make a little note here at vid.iid and do 0068 is the video ID, and the time is 1 hour, 56 minutes, and 37 seconds. Okay. And let's say what it is again, because we've taken the timestamp. I'm going to make this a 45. A conceptual member is a member that it's not actually a member. It's just a variable that belongs to a conceptual object or an implied object, right? So if we have like a first name and a last name, conceptually there's a struct called full name, like an implied object called full name, to which first name and last name would be conceptual members. Okay, that is what I mean, just describing it one more time for the video timestamp. So I think we've documented most of the variables that I'm looking at right now. There's probably more variables that I need to account for, but I think we have enough to where we can start looking at our diagrams and figuring out what's going on. But before we do that, I want to reload my shortcuts and make sure they're all in a stable state. So I'm going to reload my shortcuts here, reload this script, and once it's in a stable state, where like it's not in a stable state right now, see it says I've made some type of syntax error somewhere, global tile x chord. So wherever that is, I've screwed that up. So I'm looking through my so let's look through our shortcuts here and be like, okay, global tile x chord. It's somewhere in that message, and that is an explanation, so it should be this thing here. Okay, so did we kind of cut and paste? Did we cut and paste this, or did we just never get to it? Well, the easiest way to know if we never got to that would be to be like, well, if we type this out correctly and be like glo tx and we do means like that, it'll be nowhere if we just forgot about it. Yeah, so we just forgot about it. I can kind of see why we would have forgotten about it, because there's a lot of stuff, and we probably just got sick of it after a while. Okay. So now everything's beeping on us when we type because the script is like incompletely loaded, and now we're just in limbo. But yeah, let's just kind of do this. And this can be this is kind of tedious, but I really want to I16 GTX means 16 GTX means, sure, why not? 16 GTX means, and I really don't care too much right now. I'm just like, you know what, I just want to get this done. So we're not going to worry too much about hitting all of the different ways we could do this. We're just going to hit enough of them that it's good enough, right? So, okay, so OX quad. The first one we're going to spell exactly. OX. Okay. Paste this here. And then we'll paste this and we'll change it to Y, right? So we'll change these to Y. Change that to Y. Change that to Y. Change that to Y. No, change it. Okay. After this, the next thing we got to do is we want to make sure that when we type these things, just like when we type them to see if we spelled them correctly, when we do this means, we want to make sure that we're getting the definition for the thing we think we're getting the definition for. So we want to put these square brackets around it to kind of confirm that that is exactly what we typed, right? So we typed I16 GTX. We didn't type GTX. Here we typed I16 GTY, not just GTY. Same with this, right? We didn't just type qua. Here we didn't just type qua either. We typed OY qua, right? Or something similar enough to where it triggered an explanation, right? Okay, so now that we've done that, hopefully, I'm sure we made a few more mistakes, so I'm going to just go in here and reload this. And yeah, so a lot of things, like right now it's been 2 hours, and all we've really done in these 2 hours is kind of like look at stuff and be like, let's organize this, right? Let's document this, let's do that. And, you know, I'm not going to back off and say, well, you know, it took us a long time to do this, so this is bad, right? I'm going to say, nope, because this code base is going to be a code base that I want to have around for years and years to come. And if I want this code base to be around for a long time, then I need to take my due diligence to document everything correctly, right? To meticulously document everything. And this is kind of scaring me. It's saying I have the same thing somewhere. Okay, well, this is just the same spelling here. That's fine. We can just remove this from here. Okay, now did I do the same mistake with the X? And it does look like I did the same mistake with the X, so let's move that. Okay, let's give this another run and see where else I may have screwed some things up. And then once it starts humming away, sorting the data, we'll know, because we've made a lot of changes to this file, so I anticipate that I've made a lot of mistakes. And so this is my hackish way of checking for any mistakes I made, right? We're just going to reload the shortcuts, and we're going to have to keep on reloading these shortcuts until we find all the stupid collision mistakes we made. So I also made a mistake with OX qua. So look at OX qua. We have the correct spelling. That's good. And then in here, that shouldn't be there, right? Okay, and then the other thing is if I did it on the X, there's probably the likelihood that I also did it on the Y, right? Okay, so let's give that a reload and try to see if we can finally get these running. But yeah, it'll take a little bit of time. X temp I like that, so I did 2 of those as well. X temp I, X temp I. I don't know why I did that, because this is obviously a remainder. If I do X rem I, instead of temp, is this a unique kind of spelling? It is, so I have no clue why I did that, because that's not where it belongs. Okay, let's give that a rerun and see if, or did I auto-generate these? Maybe that's why, I don't know. Alright, so reloading the shortcuts, we'll see what other collisions we have. And once we get this kind of humming away where it's been, let's see, this is, okay, so this is, that shortcut is actually patent stuff, not related to this code. And so I'm going to put the shortcuts off screen because that's probably going to get into some confidential things, or maybe not completely confidential, but things that I probably shouldn't be showing on screen. So patent number, patent one number, patent one number. That's an interesting number. Oh, I see. We're just gonna remove those because I don't want to deal with it. And when I say patent something number, yeah, never mind. So we're not going to describe what's going on here, but basically I have some shortcuts that are keeping track of different patent numbers that I have. And one of my synonyms for finding that kind of information was wrong. So we're going to reload. That means that all of the variable documentation that we did, it looks like we're out of the woods as far as that goes. And if we are, I'm just gonna wait for this to, or we could do something really stupid like that. Okay, what the hell? Paste line, paste line. Okay, at least we have something to grab onto there. Okay, F. And what is this? It is, BY like that, huh? BY. Oh, I see. So there's no space there. Okay. Okay, let's give that a run. So I'm on line 302 of my shortcuts, so I guess I'm not quite out of the woods. I thought I was. But we're going to keep on reloading, and then once we're kind of humming away reloading this, then I will kind of go on a break here. And also it's been 2 hours, so I want to do 10 push-ups per hour. So I guess 20 push-ups as well would be a good thing to do. And try to make sure that the number of push-ups I've done kind of matches the number of hours that I have logged. So actually what I should do is I'm going to take a look at my push-ups here. So push-ups, let's make a note for the stream total. Stream total 1. And actually, properties. Stream total. Okay. So we're gonna make a note of I want it to be, you know, 20 push-ups per hour, but sometimes they start a new stream. So let's make sure that if I do more than one stream in a day, that I can keep those totals separate. And that way the math for, I just want the math for knowing this to be a little bit easier. So, and also my shortcuts seem to be humming away. So, we're gonna do these push-ups. They're gonna do our 20 push-ups, or either gonna do 20 or 30, depending on how we feel after we do 20. And then we're going to go on break and get some tea because we can't drink coffee today. Okay. Okay, so we're gonna go on break. See, red timer. Let's just make a 10-minute break. Oh, that's right, I don't have a... I can't use my shortcuts for the timer, so I'll just have to throw this here like that, really hackishly. And let's call this 10 minutes, which is like 4 extra minutes. It takes me like about 6 minutes to make tea. I have to go upstairs, come downstairs, and also make the tea. It takes about 6 minutes, so we'll do that, and then break, and maybe we can get this. I don't know where. Oh god, can we hack this? Is it in the middle of the screen somewhere? Get our bearings. Aha! Oh, no! There we go. Not the best thing, but that'll work. Okay. Okay, let's see. Okay. Alright, let's get to it. Okay, so we need to finish this formula here. And we have everything in place to do so. So aspix to diagpix is going to be this diagonal here. And what are we doing here? Let's see what this function is. Okay, glockpix to painpix. Okay, so we're actually kind of trying to take those global pixels, and we're trying to get out every single piece of information. So it looks like we have int16 versions of these. Like, as we're doing the calculations, it looks like we're like, I don't want to think about it. And I am going to say that none of these calculations make any sense to me right now. So this is just getting variables ready to work with. And then we're doing something over here where... Okay, I see. So what we're gonna do here is, it looks like what we're doing is we're gonna gather all of the XY locations first, like all the XY cell locations, and then after we've gathered all the XYs, we're going to figure out what the indices are. I think that's what we're doing. So calculate. Okay, so let's just say calculate. Gather. Calculate XY locations. How about, I don't know, calculate 2D XY locations. Okay, this is what we're going to calculate first. And as far as abstracting things into indices, we're going to worry about what the actual index values are in the next section. I believe that was the train of thought when I was doing this. So let's actually kind of formalize that and say, you know, here's calculate 2D, and then here's calculate 1D index locations, right? So that is what we're going to do, right? Because the index locations are actually going to be what's outputted. We just want to batch these calculations in where they're, we want to group these calculations by similarities to keep the code as uniform as possible within each section. So for example, we could kind of work on both of these blocks at the same time if we wish. For example, this qua thing, that is the tile quadrant. So this int16 tile quadrant is actually going to be like, if we do like, you know, to paste this and do like xy to index and get a formula going, the width here is going to be 2, right? So the width, we might want to say like, if we have enough room, we might want to say that and put a define here and say define till qua width, just so that we know that the formula right there is actually for the type of data that we're working with, right? So the width, it's a 2 by 2, right? So this is a 2 by 2 cells. and then we can undef it here. Undef till qua wid, right? The idea is that we use the exact same verbiage here, or the exact same prefix, so when we light up till qua, we can see it in all those different locations. Then this thing here, this I16 till qua, that is actually just this variable right here, right? Okay. Now the tx and ty, well, that is this thing here, the ox qua. So the ox qua goes right here, it's the remainder, but then the number of filled rows, we take the number of filled rows, multiply by how many cells are in a single row, and then we add on that remainder, and then we get a index value, right? So this is where we're calculating the 1D index locations. So we've done that. And then after we've calculated those values, we're going to whittle down the input. So we can see this I16 GTX, and we can see this just an int 16 cast of the global TXTY. And the global TXTY are our two inputs. So we can now shave off that, right? So this 256, right, it's saying that, you know, if we're here, we're not going to shave off anything, but if we're over here, we're going to shave off 256 on the X. If we're over here, we're going to shave off 256 on the Y, and if we're over here, we're going to shave off 256 on both sides. That's what this is all about. That's what this multiplication by 256 is here with the cell location, and then we'll minus it from that GTX value. Now, these values should not be negative, and since we are being kind of paranoid, we can also do this. We can also say assert, and since we are using signed values, we have the advantage of being able to check the math a little bit better and just say, you know, to check for underflow, or just assert that rem ix is greater than or equal to 0, right? That's what it should definitely be greater than or equal to 0. Same thing with the remainder y here. It should also be greater than or equal to 0. Okay, so now that we know that we are inside something here, and we've rebased, right? So no matter which one of these things we're in, we've done that subtraction, so now we can look at just this, right? We can just look at this. And if we want to, we can take this thing and say that this is hashtag dia it's a quadrant cell, I guess. Let's think about it. Till qua. Dia selected till qua. Let's call it selected till qua, just so that makes more sense, because it's like technically, like, you could think of this as dia till qua too, because there's a tile quad here, 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 and here, and oh god damn it. Okay, so let's go back to this. So I gotta get better at that. Okay, so right here, this diagram here, this is a tile quadrant here, tile quadrant, or a till qua, in terms of the diagram right here. And so, yeah, till qua 0, till qua 1, till qua 2, till qua 3. So when we have whittled down, when we figured out which one of these things we're in, we have to rebase it to be at the origin again by subtracting values. So over, god, I did so much stuff and I didn't show what it, Okay, so right here we see this OX times 256. That's that's that 256 right here to make whichever one of these we're in. We want to make this the new coordinate system, right? So that's why we have this the quadrant location in terms of x and y multiplied by 256, and then minusing from the global coordinate, and that gives us a remainder that has a remainder coordinate that's somewhere within this space here, within the space of dia selected till qua. So this diagram here, and we see this other stuff here. Let's say that this itself is a diagram, and let's kind of make a section divider here. I don't know if this is the best way to do it. and I may change my mind on this later, but let's just try to make sure that we know. Diagpix looks like it's mostly referenced in this diagram, so we can take this thing that was kind of loosely hanging there, and we can throw it in here like this. And then also, we can also use this label one more time. So that way we know exactly what we're talking about here. We're talking about this, and it looks like we forgot the underscore on that side. Okay. So now, when we're doing the math for this, we can say that right now, rem ix, rem iy is now local to this thing, right? And then we can take the at vid iid, and it is 0068, and the time is 2 hours, 32 seconds, and 32 minutes, and 10 seconds. How about, right? So now that we have this, we're going to have to re-explain for the camera, or re-explain if someone has gone to here. So once we whittle down rem ix, so right here is the global coordinate, and we're whittling it down to get a remainder. And at this point, the remainder is going to be a coordinate somewhere within this diagram here. So this diagram here. Before, the coordinate could have been a coordinate somewhere within here, and within here. And you can see that these are all like duplicate structures, right? So we want to figure out which one of these big quadrants we're in, and then subtract the appropriate value from the global variable so that we can have a coordinate within local to like this diagram here, right? So we want to, if we have a coordinate inside of here, we want to subtract 256 from both axes to rebase to here, to where the 0, 0 is, well, 0, 0, right? We want this origin here, the origin of this diagram. If we're in here somewhere, then we're inside this cell, and therefore we want this origin that's at 256 to end up being 0, 0. So you have to subtract 256 from both axes to move this thing over to here, right? So we're trying to reposition or rebase or make a new local coordinate. I don't know what to call it. I'm not very good at math terminology. And so now that we've made this little diagram kind of explaining what we're local to, we can, make the note here that, rem ix and rem iy is now local to this thing, right? And that's going to help us kind of visualize the code, because it is kind of confusing what we're doing, right? And we might want some diagrams, some pictures to help us understand what we're looking at, right? So let's make some room for this, and yeah, that's good enough. Okay, so now that we're local in here, the next part we can subdivide is, which one of these things we're in, right? But to figure out which one of these things we're in, we actually have to figure out, well, what size are they, right? Because if they're these big sizes, then we don't have to do any subtraction, because the origin is already at 0, 0. But if it's one of these smaller size cells, then the origin is, somewhere in the middle, and we got to subtract, I believe, 128. Yeah, 128 right here. So let's look at this. So we do, to get the diagonal pixel xy, we take the astpix to diagpix. So we see astpix, and what does astpix mean? So you have a nice little table here, and astpix, offset subtile pixel, right? So offset subtile pixel, so that means astpix is so astpix, and xy location local to this diagram. Local to an offset subtile. And then, we could say, astpix means, we should have a definition for that by now. Ooh, we don't. Oh, boy. We did all that work earlier, and it looks like we missed astpix, maybe? Let let me just try astpix and see if I can find it. We have the correct... Oh, it's not astpix, it's astipix, right? Yeah, it's not... Got ya. Okay, you know what? So if I spell astpix wrong, I should probably correct myself. So, astpix right here. That's a misspelling. We'll consider astpix a misspelling, right? Because I thought it was because when I was looking at this, I thought this was aspix, so it's astipix. So if we do aspix, we're gonna say you mean astipix, and I in the middle. And also that means we tried astipix beans and it didn't give us anything. So if we do this, we want to say we were confident that we were spelling it right, but we weren't. So aspix, a typo misspelling of astipix. Alright. Okay. So I just want to put those corrections over there. Okay, so now that I realize that, astipix means, so we should have a nice little definition here, offset subtile pixel. And we can actually just remove this little thing here, and then astipix, right? So astipix is like any pixel in this region, right? Like any pixel anywhere in this here, right? And that's why we can get the diagpix from it, right? To get the diagpixel location, which is just kind of a it's not actually the diagonal in the sense of the length of the leg of a triangle. It's because we locate this diagonal by saying we're going to use the same amount on the x as we are on the y. That's what we mean by diagonal here. So yeah, we got this function that's going to give us that diagonal pixel, and it could be different on the x or the y, because you can see that we did diagpix, right? Here's how we're going to calculate diagpix, and then diagpix y is similar, but we look at the y-axis and look at where these partitions are, and then it's the min of whatever that is. So you could be like over here in these little things here in terms of the y, but on the x you might only be, you know, like over here somewhere, right? And that would mean that you're in something over here, or you're in something over here, right? Well, if the y was over here, then and the x is over here, then it means that you're probably in a cell over here. You're not in a cell down here, right? So we don't want to say that the diagonal is something down here. We want to say the diagonal is this thing. Okay. Let's look at the diagpix. So we take we do the two calculations with that remainder. So we might also want to make a note that rem ix rem iy equals astipix at this point in time, at this place in the code, right? At vid iid 0068, and the time is 2 hours 39 minutes and 51 seconds. Let's just do 40 minutes. 40 minutes, 0 seconds. So say this again. Rem ix, rem iy equals the astipix at this point in the code, which means, in our diagram, that rem ix, rem iy is somewhere in this local diagram. It's any pixel that could be anywhere in this region. Now we have to figure out what the diagpix value is. So we first need to get that the x and the y, and then we take the min of that x and y to get the diagpix value. Knowing the diagpix value, we can now calculate one of these index locations, because diagpix is an xy, but x and y need to be the same. So if we go up here and we look at what we need to find the tile exponent, right? Now, the tile exponent, hold on. I'm not sure if I did that quite right. Because the diagonal pixel is not going to give us a... It's not going to give us an exponent value. So, okay, so we actually have to convert that diagonal into an exponent value. Okay, fine. So we need to convert that into exponent value. So let's see what our helpers are here. So we got the diagpix here. And we have tile exponent to diagpix, but do we have diagpix to tile exponent? And it does not look like we have that. But that is kind of the function we would need. So these are generic helper functions, and these are like conversions. Now max coordinate. No, that's fine. Yeah, so I think we need the inverse of this thing here. We got like PAINT5D, CTO, GlockPix. Okay, yeah, so we're gonna consider that a conversion function. And we're gonna put it, we're gonna pair it over here, right? So, I see that we're kind of, you know, using a U08 here. Now, once we're in here, this should be a 0 to 255 coordinate, right? So, we see this as 256, so the range would be 0 to 255. So that makes sense. But we need to make certain that we don't pass it the wrong type, because right now we're working with int16s. But let's keep the signature, you know, complementary, right? Because it's the inverse of this function. So let's not be tempted to... so diagpix converted to tile exponent. So the tile exponent, or the tile size for that diagonal value. Right? And because let's just do it the most naive of the ways that we can. So let's do a switch on diagpix. And we have different cases. So case 0, then the tile exponent equals 0. And then we'll need to break. We have enough room where we can just write it like this, I think. Now, if it's not 0, then, right, these are going to be very exact values, right? There should be no... Well, I mean... Yeah, we're going to assume that this... There's other ways where we could do this, where maybe we're, like, in here somewhere and we want to figure out what the diagonal is, but we've already kind of had the formula. That's astapix to diagpix, right? But right now we want to figure out, like, the exact tile exponent value. So we don't want to do this again. We want to do... Yeah, we're looking at exact values now. So we have 0. The next thing here is going to be 256, right? So we have a lookup table, but let's just do tile exponent equals, and let's do this. Let's do this plus 256, because there is going to be a very obvious pattern here, and we might as well just do it, right? So so after 2, it's going to be 256 plus, guess what, 128, right? And so let's kind of keep that pyramid going. I know we made one of these pyramids somewhere else as well, but let's just put it here as well, right? Let's not try to reuse the code if we want to get a refresher on what's going on, and also it's less mental indirection anyway. So half of that, right, 64. And also it'll help to check whatever math also uses the same kind of lookup table as a redundancy to make sure it's correct. So 4, instead of 64, we're going to do half of that, 32. And it's just going to get pretty long now, isn't it? So what we could do is we could do a a shorthand for this variable name. So define te till x, right? Tile. Tile. It's a tile size exponent is what it is, if you think about it. And then down here, like, even though this does apply really to a very specific function, we're gonna keep our defines located on these sections. Even though it is pretty far away from where we're actually using it, that's how we're gonna do it, just to keep the code nice and neat. Will I ever gut this later? Maybe, yeah. I mean, maybe, but I gotta have some consistency to how I do things. So right here, we're gonna say that, you know, return te, and the te is tile till x, right? And then we can also do a little assert right here. We can assert that these are the same thing, right? Assert te equals till x, right? Should be same variable. At same var. Alright, they're the same exact variables. They should be, at least. But in case we made a mistake, we can have a little assert there, in case this define is not the define we think it is, right? Now, we also have to define it up here, like declare it. So it is a U08 till x, and it's going to be equal to, how about 255? So that's the largest value it could possibly be, and it's invalid. Invalid trap value. In fact, a lot of exponents are invalid. Like, we only go up to 8 or 9, depending on what kind of rendering system we're using. So we could just do, like, 230, like that. It's still out of range, but it's a little bit different of a value than what we usually use, right? So something a little bit different. Because 255 is probably all over our code. So something like that might be a little bit easier. Actually, let's do 222, right? Just because then it's a little bit more obvious that it's like this pattern that we intentionally put there. Now that we have this, what we can do is we can just call this TE for tile exponent. And for break, we're gonna just say that break is BRK. I know that we're only saving like one character, but okay, we're saving 2 characters. But this is getting a little clustered, so I'm gonna do it. So BRK is for break, yeah? BRK is for break. Okay, and then we can kind of replace this with BRK. And you know, we could get really, we could get crazy, right? We could go cast for case. And some people are gonna look at this code and completely hate me for doing this. Cast is for case. Okay. So, cases. But I just want more room because I do not want to have to reformat this, right? I want to be able to keep this table nice and terse and spaced out how I'm spacing it out without having to reposition things. So we already know that, okay, we got this 16 and we're already running out of room again, right? So if we go put this all the way back here like this, right, we got this 6. Well, that's plus 8 now. And like maybe we have one more line, but we still need more stuff. So this is 8 and this is plus a 4. Yeah, so we're out of room again. So we got to think about, well, what do we want to do to this, right? Because no matter how many characters we say, we've made this basically as terse as it can possibly be. So we're gonna have to fix that. Let's do def for default. And just say error. Invalid diagpix input cannot convert. Okay. And I don't think a default needs a break. You just write it like that. If we're gonna do that, if we're gonna be crazy like that, yeah, we're being a little bit crazy. And we'll hate ourselves for it, but at least it's only local to the section Unlike sometimes when we got crazy and we decided to do it for the entire file or the entire library, which was completely idiotic. So even though you might think this is kind of idiotic, I've done worse. So let's do pluses like this. Because if we get rid of the, because if we kind of get, we still have a space where you can see these columns, but now we're condensed enough to where we can get some of these last statements in, right? Because we need this +4, we also need this +2, and then we also need a +1. And do we have just enough room, or we have like one too many characters here? What do we want to do? I'm thinking just move this over like that, and that's kind of ugly. But then we're good, right? Then we've smushed everything together, but we've smushed everything together, but we have we smushed it all together. But the idea is that the most important thing here when we're looking at this is these things here. We want it to be absolutely obvious that these things are here, right? These numbers are here like this. And we're not going to hard code, so these should be compile time constants, so we're not going to actually see these numbers in the code. The compiler should be smart enough to know what this evaluates to, I believe. I could be wrong, but I don't think I am. And we could calculate these and hard code those numbers in, but then we would lose the pattern, right? And the pattern here is is very important, right? To understand, well, what is the pattern that we're looking at, right? And we see this, and the pattern is describing this, right? Where it's 0 plus 256, and then we want a plus 128, which is half of that, and then we want a plus 64, which is half of that, and etc., 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 right? So the smallest tile exponent, the smallest tile size is at 0, 0. There's no actual offset that needs to be done. Now, these numbers here need to be fixed. So we see 0, 1, 2, 3, 4, 5, 6, and then we have to go 7, 8, 9. And I don't even know if the compiler would catch us if we made such a mistake. Now, what else? We have this default error. We can also do, if we want to be really paranoid, you know, we think that error is not going to catch the problem, we can assert that diagpix is less than 9, or less than or equal to 9. And if we want to be really paranoid, we got to do that. We can do this I32 diagpix, cast it to int32, and then because the compiler knows what we're up to, +0, right? Just ridiculousness, right? But the thing is in case I change the type of the signature later, I want to be able to look for underflow. So in the case that this value is less than, we want to assert that that value is greater than or equal to 0. Okay, so there we go. We got this crazy assert. We can put that down there. We could probably glue it down. We could kind of glue this, if we could. We could just throw it over here like this, like we're crazy. We might want this structure here, this kind of pyramid. We might want that pyramid to have some room to breathe, right? So that when we're looking at this, you know, I'm going to call it a pyramid not of doom, in reference to the anti-pattern called a pyramid of doom. And that's kind of weird looking, but I like it. I think that helps me kind of see, hey, look at me, look at me. This is the most important part of this function, right? We're trying to convert this, most important part of the function is this. Now, did I even write my switch statement correctly? I don't know, I don't write switches too much, so it's like, oh, I don't write switches too much. Oh, here, let me write it in this completely crazy way, even though I barely write switches. But there we go. There's my switch. So at same var, I don't believe I have used this annotation in my code before, so we're going to go over to our hashtag stuff and just be like, hey, is there like a at same var thing here? And there is not. So we're going to put that in the documentation as well. Okay. And then we can make a note of what at same var means. Actually, I'm going to do it like this, just because I want to actually be able to see it when I'm looking at it. And now we have it in two different ways, but whatever, this is good enough. Means that the two variables you are asserting for equality are actually the exact same variable. Quite literally. One is probably a macro, and the other is not, and you are trying to make sure they are such. Now, if that's really what I'm trying to do, I'm trying to say that they're the same var. What I actually am trying to say, if that's the case, then what I'm actually trying to say is that the address of both of these is the same, right? Because if they're actually the same variable, then their addresses are actually the same, correct? Because they're the same variable. If they're the exact same variable, quite literally the same variable, not the same value, but the same exact variable, then what I'm really trying to say is this. So now this is kind of a pointless assert, right? Because they're the exact same memory address. Of course, they're going to be the exact same value. But I'm not going to remove it, you know, because it's a redundancy. It gives you more context for what I mean by same var, right? You see this and you're like, oh, same var. And you're like, oh, really the same var, you know? So, right, so when you're looking at these addresses, you might expect to see same address, but it's the same variable. Or we could, let's see if we have room. Same var, same address. We don't have enough room for that, so we'll do this. ADDR for address. See, now we're just getting carried away. Let's just put it over here. If they are indeed the exact same variable, then they should have the exact same location in memory. All right, that's all I'm trying to say there. Now we can also make a note at vid IID. It is 0068, and the time is 2 hours, 59 minutes, and 17 seconds. So once again, if they are indeed the same variable, they will have the same address. So right over here, same var, same address. We take the address of this macro and the address of this macro and the address of this variable, and they should be exactly the same. And I'm just saying that this thing here is actually just shorthand for this. And we just want to make a assert there to make sure. And the reason we've done that is because this little table we've made is pretty compact, and we had to shorten the word case, we had to shorten the word tile exponent, and we had to shorten the word break, just so that we could kind of fit this in here with the proper indentation. Now that we have this, diag picks to tile picks, we got to be like, well, are we using it anywhere yet? Are we using it anywhere yet, or did we just say, oh, that's the next thing we need, and we didn't even call it yet? So we didn't even call it yet, okay. But we know where we need it, right? We have the big macro here, or we had something somewhere where we said, oh, we have this error here. So this diagonal pixel here, right, diag picks to tile exp, we can take this and do diag picks here, diag picks, And then we could also, if we really wanted to be weird, we could also kind of do this. We could be like, I don't know if that's a good, I don't know if that's good, but you get the idea, right? That I'm kind of like lining this up with this so I can kind of see what's going on there. What might make more sense, if we really want to do something like that, we could do this here. We'll take this, and we already have kind of macros here. Oh yeah, we have macros for this location. So let's just do define, and we don't even have room for this, do we? Yeah, like it's gonna be huge, right? Because it's gonna be like diag pix c2 till x, right? Okay, we don't have enough room for that, so we're not gonna do it. We're not gonna do it just because we don't have enough room. Yes. So diag pix to tile exponent, and now that we have the tile exponent is just gonna tell us how big these cells are. I feel like I am missing something, right? We got this diag pix. Ooh, you know what? Because we have to subtract the... Don't we have to subtract the diagonal pixels? Yeah, we have to subtract the diagonal pixels after we get them. Like, we have the tile exponent. That's good and all. But tile exponent, first of all, is this thing. Don't we have an int16 version of tile exponent for some weird reason? Because we did everything and we're like, here, let's make everything an int16 before we convert it. Yeah, we do. And that's just because I don't want to deal with these pointery things when I'm doing my math as well. Because that could confuse me. So I'm going to keep on doing that and say that, yeah, tilex, you're this thing. And the other thing is that this right here, diag pix, it needs to be a UO8 value, right? And diag pix here is probably int16, right? Int16 diag pix, yeah. So we need to, let's just do this. This is gonna get weird. We need to make sure that we cast the result of this. So, U16. We need to upcast this to U16. And over here, this diag pix, we need to cast this to, we need to downcast this to UO8. And I am gonna like make more parentheses than I need, just because I'm paranoid that I'm gonna get it wrong, that I don't know my operator precedence or whatever. I'm paranoid that maybe that I don't know that, right? So diag pix, it needs, like if we look at the function, right, it's 8-bit for everything, right? 8-bit for everything, yep. So that's actually wrong though, right? Because this diag pix, I have this 256 plus this plus, oh no, that's not wrong. This is going to be like 1 less than 255, right? So let's copy this for a second. And let's just put that into a calculator and see what that is. That should be like 254, I believe. Oh god, no, it's 511. Oh, okay, whoa, okay, hold on. That's 511. Okay, we've done something horribly wrong here. Our math is totally off. So if that is 511, then what are we doing wrong here? So this first thing is not 256, is it? So this here, we need to label the size of that, but this is, yeah, this is 128 right here. The whole thing's 256, but one of these is 128. So let's label this again. So let's label this as, 128, and this as 256. Okay. Because we screwed that up. And we explained it completely wrong. Yeah, so this should be... So also we have more room to do stuff, so that's cool. So we could probably... Well, no, because, let's see, 1, 2, 3, 4, 5. We have 5. 1, 2, 3, 4, 5, 6, 7, 8. Now, even though we have kind of more room, we don't have that much room, right? So... we don't have enough room to Now, we might have room to say, what's the most important thing here, right? Do we just want to say, like, could say tile X like that. Like, what's the most important thing to actually follow the logic, right? And the most important thing to follow the logic isn't these; they're just shorthand. When I'm talking about following the logic, I want to see like where all the variables we're using are used. So this would be the most important thing, because when we highlight it, those points weren't going to be highlighted. We had that mental indirection. So since we have a little bit more room to work with, I think the most important thing that we could change to get more information is change this. We have this one extra space here, but I see we kind of did this weirdness over here, so we can do that. And there we go. So there we go. We've kind of fixed that up. So now I'm expecting this to be like instead of being 255, I'm expecting like 254, I believe. So let's just check that in a calculator and see if that is what we think it is. And it's 255 exactly. Okay, well, not what I expected. But I'm going to guess we never get to 9. Yeah, we never get to 9, though, right? We only go up to 8. Oh, yeah, that's right. We only go up to 8. Hold on. Yeah, because if we look at... I think we have some enumerations for this or something. We only go up to 8, right? Oh, do we only go up to 7? No way. We only go up to 7? That is suspicious. Because the math would say otherwise. The math would say that, hey, here's the point at which you only have 1 pixel. Here's the point at which each thing is 1 pixel in size, correct? So why do I have that? So I'm going to change this back to TE for a second. Okay. I'll just make a note that, you know, this is TE right here. Alright, we want to be like, we want to be like this. Like, this is TE. Pay attention to me. I'm TE. Oh, okay, okay. I see. Yeah. Oh, yeah. Okay, yeah. That's why. Because look, when we deleted one of those things in our pyramid, when we deleted that 256, all of a sudden we have these 2 entries here, and we need to like shift this whole table up. So we gotta like take all of this, and we need to paste it up here. That's what we're missing. So now that we've seen that we've been stupid about it, yeah, and it should actually be, we have this case here, 8, but 8 is actually invalid because it's like the last pixel. It's only 1 pixel. There's not 3 of these pixels. There's 3 of these pixels, but there's only 1 of these, right? So as you're going into, so hold on, let me highlight this for a second because we're going to come back to you. As you're going through this like mip-map structure, eventually you get down to where this is 1 pixel, this is 1 pixel, and this is 1 pixel. And the final depth you get to right here is just 1 pixel, and you can't use that because you don't have 3 layers. Like, everything has 3 layers until you get down to this 1 pixel. That's completely unusable. We can't use that. So that 1 pixel at the very end of this like map like structure, it's this thing right here. We can't use that level. So this thing here, this diagpix thing here, this should actually be 7. It needs to be less than or equal to 7. And what we can also do, if we want to be more paranoid, this assert here, we can just say, you know, assert that, oh, also we have static assert, don't we? Static assert, yeah, in C, in this version of C. I know there's a static assert, I just don't have a shortcut for it. I'm gonna change that though. So we could assert that, you know, this is equal to 7, right? We want to know what that magic number is, so we could kind of throw it in there as well. So let's look for static assert for a second, because I know I have static assert in some code I already wrote, and I know exactly where it is. So hold on. I'm going to write static assert in my shortcuts. Static assert. And also I'm going to do assert static, and assert static. I know you can't see this. Okay, so let's go into our library chain, or not on our library chain, but I believe it's in F macros we do this. So F macros in the top, we have a static assert somewhere, don't we? Yeah, static assert. That's what static assert is called. And it looks like it needs an assert condition and then a string or some type of message or something like that. It's probably not a string. I just wrote it that way. So static assert and then condition some var equals some var, and then err msg. And I don't think a static assert needs any semicolons because it's a static assert. It's kind of at the macro level, but it looks like it doesn't complain to me when I do it, so I'm gonna do it that way, even though maybe that's a bad thing. But I'm gonna roll with it and do it that way. Okay, so now I have static assert in my shortcuts. It's ready to go. It's not wired. It's not loaded into my shortcuts. It's just in the shortcuts file. But yeah, so right here we could do static assert, right? So static assert, and then just say, hey, you need to be, equal to equals 7, right? Now this is kind of long, so what I'm going to do is I'm going to take this thing and I'm going to go SA for static assert. And then over here, I'm just going to add more macros. SA is static assert. And then down here, we'll just say undef SA. Okay. So we have a static assert. Right, so when we're using this 7, this magic number 7, that's what it is. This is like, I don't know, we're acknowledging that there's this like +1, that this is the end of the pattern, but we want to be like, well, but, just because that is there, and that does kind of logically complete the pattern we're looking at, it's still an error, right? Because, all right, so assert that diagpix is less than or equal to 7, right? And we're going to assert that the 7 equals this. So 8 is only 1 pixel, and thus not useful. Okay, so at vid iid 0068, and the time is 3 hours, 13 minutes, and 15 seconds. Okay. So what I mean by 8 is only 1 pixel, and thus not useful, I'm talking about this case right here. And when you do this math like this, if we look at PAINT5D and we look at the diagram, right, this is our 0. To get to 128, we go like this, right? And it gets the origin of here, right? And to get to the origin of the next thing, we got to go 128 plus half of 128, which is 64, right? And that's this line right here, right? This is the third exponent level, 0, 1, and 2, because when I'm talking about adding this, I'm talking about getting this origin down here, right? And then we continue the process, but eventually we get down to this last cell, and this last cell is only 1 pixel, and it's not useful. At exponent level 8, we only have 1 pixel, and that's not useful because we want these 3 different sections for 3 different layers of data, and at that very last pixel, we don't have that homogeneous data anymore. We don't have that homogeneous structure that we can work with. So that's what I'm talking about when I am making this commentary right here. So I'll just leave it grouped there so you can be like, oh, this video ID corresponds to this comment, and I just explained what that's all about. Okay. So with that, I think we have like a good lookup function, right? It takes a UO8, it returns a UO8. What other asserts could we do? So this diagpix, I mean, if it's not one of these, then we don't really need a range check on it, right? It's just like, we should probably, if it's not in this range, why would we need an assert, do we have any asserts on it? We even have an assert here. Oh, hold on. Diagpix is this less than 7. This is not diagpix. This is this thing here is not supposed to be. This is tile exponent. What am I doing? So this is tile exponent here. Same thing with here. That's tile exponent. My bad. So we could do an assert on the, if we really wanted to, we could also assert that diagpix is less than or equal to 255. Oh, well, that doesn't matter, right, because of the U08. Once again, what if he's changed the signature? So the compiler isn't going to let us do that, so we're going to have to do this. We're going to have to do this. We're going to have to do a cast. We're going to have to do diagpix. We're going to cast it to a int32. And then we're going to add 0, right? And then we're just going to say, compiler doesn't know that we're doing this. And then we're going to say less than 255. And the idea is, in case type signature changes, right? So right now, it's still in that range, but if the type ever changes to something bigger, we want to make sure that we can catch this. So that's why I'm range checking something that can never even be, this type right now, diagpix can never be over 255. It literally does not have enough bits to be over 255. But in case we change this to a 16-bit or a 32-bit or a 64-bit later, I mean, likely that'll never happen, but I want that kind of robustness in my code, so we're going to do it. Okay, now I think this function is actually ready to go, even though we've, like, second-guessed ourselves so many times. Now that we have diagpix in this thing, what would be nice is just to have, like, well, let's just make sure that it's referenced here for a second. Okay. So let's make sure, let's actually go into, do we have unit test code yet, or have we kind of been like all over the place? No unit test. Keyboard handler stuff, math. It's all in here, huh? So I don't think we have unit test. The one way we can find out, we're going to type unit test like this in camel case. That's how I usually type our unit test. Also for the sections, we usually type it like this. Okay, in neither case do we have something that says unit test. So down here, we're going to start to make some unit test code here. Before we forget, because there's like a lot of different components that need testing. And we don't want to forget, we don't want to just test the main things, right? We want to test the helper functions too, right? Because if the helper functions fail, then we can't rely on, well, if the helper functions fail, then our main functions probably will fail. And even if our main functions don't fail, they are erroneous as far as I'm concerned, right? If the helpers aren't correct, then the function that uses the helpers aren't correct, right? So this function we want to test, so we're going to do like a U32 AAC 2020 PAINT5D unit test. And I need to remember that it actually needs to take void, right? It needs to take void. If it doesn't take void, we're just saying that we don't care. Or we unspecified. And that could create some problems. Well, it'll probably most definitely create problems for us. Okay. So, and I don't even know how you do an unspecified function and then pass it arguments and then use those arguments. I don't even know how you would do that. I'm guessing you could do it with like something veridic, maybe? I don't know. I have no clue how that works. Maybe it makes sense if you're writing a little bit of inline assembly. Maybe it makes sense. I don't know. That's the only way I could think of it making sense, that you use you're using assembly with the function in some weird way. Or I guess what you could do is if it had an unspecified number of arguments, you could call it as a function pointer. I have no clue. I have no clue why they do it that way. I should probably learn. Okay, so let's do AAC 2020 PAINT5D unit test code. Right. So I'm naming it very similarly to this right here, so that I can, find it, right? And I don't know where I guess we want the high-level overview to be at the top. That would make the most sense. And this is going to be void. This is also going to be void. Because we're just going to halt, really, if we have a mistake. And this is not void. This is going to be a U32 called U32. We're not actually going to use it. We're just going to say if U32 and reserved for future use, because we've been doing that everywhere, and we're kind of stuck doing it for now for consistency. Okay, so now that we have this, we got to like write this function. We got that function there. So we just want to do something like we really only need to go through like some type of index, tile exponent. We can actually have the variables themselves. So we could have like till x equals, you know, call this, right? And how about for the tile exponent should be between 0 and 7, if we look at this. Yeah, this thing here. And so we could do right, define max exponent, and then use this. Now let's just not... Okay, so max exponent, less than or equal to max exponent, tile x plus plus. Right, I get the tile exponent. Do we have enough room to indent properly? Yes, we do. Excellent. Once we get the tile exponent using the... this is wrong, right? Let's paste this again. Diag_pix. We want to get diag_pix, so we want to do the opposite, so the till x converted to diag_pix. And then we can use this tile exponent here. We're going to use the tile exponent to get the diagonal pix. We'll use the diagonal pix to get tile exponent check, right? So tile exponent's CHK, because it's more specific, right? If we're going from general to specific, well, this is tile exponent, you know, actual, and this one is the check value, right? And then after that, we could do one more thing, I guess, but does it really matter? If we can successfully convert back and forth, it doesn't matter that we started with the tile exponent, I don't think. Now, it could, if you're doing... We can't even convert back and forth with diag_pix anyways, because diag_pix could give us values... that gives us pixel values, right? That may be between 0 and 255. And when we're testing the very specific cases, we have, you know, 0 to 7, right? There's a pigeonhole kind of thing going on here. We could not do this the other way. We couldn't go for diag_pix equals 0 to 255. It wouldn't work. This conversion has some information lost, right? Because we're funneling down a pixel value into one of these enumerations. So we can definitely take a tile exponent, convert it to a diagonal pixel, and then we can take that diagonal pixel and we can convert it back into a tile exponent. We can do that, we just can't do the flip-flop thing of that and do diag_pix to tile exponent and tile exponent to back to diag_pix and cross-check the diagonal pixels. They won't match each other because it'll be like almost like as if we floored the diagonal pix value. It just won't work. So let's call this we'll just assert, right? So no, not assert. If tile exponent is not equal to tile exponent, CHK, then, you know, error, diag pix c2 till exp test fail. Unit test fail. Alright, we're failing this unit test. As far as the macro for ERR, we got to define that as well. But this is all we should need. Now, we do need to declare the variables, don't we? For the math here, we're using U08 values for both tile exponent and the diagonal pixels, and also for the check value as well. So tile exp chk, and then U08 for the diag pix. Okay. So yeah, I'm satisfied with that. Now, in order to call this, we need a for declaration. So extern void that with a void. Now we still have another problem where it's like, oh boy, this got pretty long, but I do want to keep my for declaration directly above. So what we're gonna do is we are going to, I don't know what we're gonna do. I guess we can be really obtuse about it and be like define ext as extern. We could define VOD as void, which is like, what? You're just saving one letter, but we're getting kind of crunched here, so even though we're saving one letter, it'll probably save us. It'll probably be enough to get rid of this, right? Because then we can do like ext VOD, right? And this takes VOD, right? So yeah, that is weird, but it's like I want to stay inside that column limit, so I will end up doing like really weird things to make sure that I can keep within that column limit. And UTC stands for unit test code. We could also write that in our little index. We have a little index here, right? So we could say you know, this isn't really an identifier. This is more like a prefix or suffix index is what this is. We can just say, you know, UTC is unit test code, right? Unit test code. That's good enough for me. Okay, so we're calling it. It has a for declaration, so we're good there. Let's dash line I1 x64. Let's kind of separate this up and make sure that we can see what we're looking at. Okay, so we need some more defines, right? We need to define U32. I know we need to define int 8, I08. And what else do we need to define here? We don't have an air macro, so we got to define that as well. So define. We don't have a define for that. Just go. We've been using it a lot, so you'd think we would by now, but we don't. So this. Oh well, the reason we don't is because it changes depending on what file we're in, right? So the air macro for here is going to be AAC 2020 PAINT5D halt, right? Let's make a little checksum so we know how much to put. Oh, hold on. Let's see if there's anything else. No, that looks good. That looks good. Okay, yeah, that's good enough. Yeah, that is everything. It's not good enough. It is exactly. It's exactly what we need, right? We have all the macros. So, good enough sounds like there's more that could be done, but no, we've done exactly what we need to do. It is all accounted for. So there's 5 things. So this is 3, 4, and 5. Then we can take all of these, and to make this a little bit easier, we should probably keep all of these outside of here, outside of this region. Because if it's in that region, then it makes it a little bit harder to do that column selection, doesn't it? So, okay. Now that we can kind of easily column select, we can go over here, and we have 6 things? I thought we only had 5. Or is that because we couldn't easily column select and we missed something? It looks like we missed something, because it says 6 right here. I don't know why I said 5. Probably because I'm not paying attention. Okay, so undef this. Okay. 1, 2, 3, 4, 5, and 6. Okay, and we're gonna have to do 20. Let's just keep on doing push-ups in groups of 20, since it seems that doing them every hour is not always enough, is a little bit too much of a distraction. Okay. So we tested this helper function. What other helper functions can we test? I know we're kind of like all over the place, but what other functions kind of need, what other functions need testing? What other functions need kind of some type of certainty that they are working properly? So I see that we have this max coordinate, and there's not really anything we can say about this, right? It's just, 128, 64, 32, right? Depending on the tile exponent, right? Well, you might want to say is, if we look at this 128, yeah, that makes sense. We could, if we wanted to do some redundancies here, we could test this. We could do, if we really want to test that and add some redundancy, so really not, it's really not a test, it's just like it's just adding something to, so a test isn't just about checking your math. A test also gives some redundancy and rigidity to the code, where I know this is pretty trivial, so it doesn't really matter to test it, but let's say that one day somebody goes into that function and changes it. This will kind of help my code break if something accidentally gets changed, right? Because now it has to be changed way up there and way down here, right? And the likelihood of that accidentally happening in 2 places is much reduced. I don't know what the likelihood is in an exact percentage, right? I don't think you could actually ever quantify that, just because it's such a rare occurrence, and we're talking about my specific code base. So, but we're reducing the chance, right? We know we're drastically reducing the chance, and that's what matters. We know this takes void, and we need to separate this. Then we need a for declaration. So we have this ext vod whatever. It looks like we were in the business of getting that ready. And it's just as long as the other one, isn't it? And I don't think that either of these use each other, so it doesn't really matter which order we test them in. We can just put them in the order that we kind of declared them, right? Okay, cool. So to run this, we need the function again. So it's AAC 2020 PAINT5D, and then this, right? Tile exponent to this maximum coordinate. So max core, I don't know, assert 0 equals, the maximum coordinate for this should be like 127, I think. Yeah, these are the maximum local coordinates, and yeah, that would be correct. If, because at this tile exponent for this system, only for this system, for other systems, we might abstract the data differently, but for this system, that's how it goes, right? So 127, and then we need to go 1 all the way up to 7. 1, 2, 3, 4, 5, 6, 7, right? So and this is going to be 63, because we're going to take 64 and divide it by, we're going to take 64 minus 1, right? This is 31, because we're going to take 32, we're going to minus 1. This over here is going to be 15, because we're going to take 16 and we're going to minus 1. This over here is going to be 7, because that's 8 minus 1. This is going to be 3. This is going to be 3, because we're going to take that 4 and minus 1. This is going to be 1, because we're going to take 2 and we're going to minus 1. And this right here is going to be 0. Because we're going to take 1 minus 1. So this is where we have just one gigantic tile, and this 1 here means the coordinate is 0 to 1. So this is where we have 4 really big tiles, and this is where we have just one gigantic tile. So that's all we need to do for this test. And we'll just keep these asserts in here. We won't even, you know, that's good enough. I'm satisfied with that. I don't want to have to like make variable names and whatnot. That's all we need to do. It's just a simple redundancy to help us catch kind of stupid mistakes that we're making. And we can take these functions, and I actually do want to make a type def for this, because if you look at this, if we're searching for usages of this function, it makes it a little bit harder to look through the code really quick, right? Because we don't want to stand here in this section, right? We see this section, we don't need to see all of this all the time. So for that, we're going to say, you know, define, we can do, no, let's just say fun function. We'll call it fun for function, yeah. That's our function. Undef. Fun. Yeah, good enough. I mean, it does make it a little bit, like, weird to look at. But you see, now we see this here, and we only see one instance of this. And that way, when we're looking through the code, we don't have to get distracted by that, right? We can find all the highlights of where it's used, rather than, you know, see how we can quickly go through the code and see all of the points at which we're using that function. We'd have a little bit of trouble with that if we kind of didn't use this macro here, and then we had to click. I don't want to be able to have to do that. I want to just be able to go next spot that is relevant, right? The next region of code I would like to look at. So here's the actual function. Here's where we're using that function. Oh, you know what we want to look at? We want to look at where the function is and see, like, well, what other helper functions are in here that we want to look at, right? So, you know, we could, let's just kind of copy some of these things into some notes to be like, hey, I want to test these. So I want to test this thing, so I'm going to copy that to my notes. I want to copy this. Oh, actually, here. Let's put this on a thing that you can actually see, right? So I want to test in a little file that I'm going to throw away later. I'm just going to take these and kind of collect them. So let's just kind of go through some of this code and be like, what do we need to test here? What is in here that requires our testing, right? So this max coordinate thing we already did. Tile exponent to diag pix and diag pix to tile exponent. We already tested the conversion back and forth between that. I don't think we tested this. We could have, but I don't think we did. So let's throw that in there. So the PAINT5D Glock pix to pain pix or whatever, eventually we have to test that. So let's, this is kind of one of those bigger functions that, you know, we're working on, but it has a complementary function, does it not? Yes, it does. So we need to, and this is like a conversion helper function. Like, it's huge, but it's like a conversion helper function for PAINT5D put and PAINT5D get. So PAINT5D put and PAINT5D get also need to be tested. Okay, so we've collected everything that needs testing, but I need to go on a break. So we're gonna, our shortcuts are reloaded, so we can actually go to the timer I want to go to. Gonna get 15 minutes, and if I have any extra time left over, we're gonna do some push-ups. Okay, so I'll be back. and spam, huh? Okay. So I am peeling an orange right now. So here's what we're gonna do. I'm gonna peel this orange, and then, because I'm eating, I should probably do my push-ups. Seeing that I have some more food, yet I have not done any more push-ups. And I see we're at 4 hours. And if we're at 4 hours, then we should have done 40 push-ups, which we have not. So let's take care of that after we fill this up with... Okay, yeah. So we're going to do our 20 of the push-ups that we owe. So let's look at this. Push-ups, we've done 20 so far. We need to do... We're almost at 4 hours, so we got to do 20 more. So I'm going to do those right now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 2 extra just in case. Okay. Okay, so all right. So we are in the middle of kind of stubbing in test code that needs to be written. Even though we don't have all of the code written, it's just our code's all over the place, and we want to kind of keep track of what's where. And starting to write these test functions will help us keep track of everything we've written, because we've written stuff all over the place. And yeah, so let's see. Interesting. So we have some functions where moving the camera and whatnot. Some of these functions we're not really gonna... Well, I don't know. I mean, we could probably... test them. I'll think about it. Yeah, I'll think about it. I guess maybe we should. It's gonna make a lot more test code, but you know what? We did say that we wanted, you know, a code base that is robust. So let's take different functions here, and let's put them onto our stack, our clipboard stack, so that we can write test code for them later. Because even though we think a lot of this stuff, key in, we're not going to test. It's input handling. We're not going to try to emulate input, and then, you know, what the input does could be subject to change. So we are not going to try that. We have public and private version unit test. Okay, so let's dump the stack of clipboard stuff. Oh, almost lost it. So yeah, we have this nice little list of things that we would like to test out, right? And let's just kind of stub in the test for all of these things. Yeah, let's do that. So, some of these utilities are going to be pretty simple. So we take this like min16 and unit test code, we can just say, you know, min16, right? And then we could go, you know, void, and then down here, some type of min16 code. So let's, if the tests don't take too long, we'll try to fill them out as we go, I think. So this one, done. Or it's not done, but we have it stubbed in. And let's just say that, you know, let's just assert that, you know, that when we take the min16 of, you know, 3 and 7, that equals 7, or that equals 3, oh boy. Okay, just a little smoke test. And then let's just assert that, the min of 0x00ff and 0x ff. So it's 16, right? So 16 is 2 bytes. So therefore we have 2 bytes here. And that's all we should need. This is going off the screen, so we're going to have to do like a define. I'm just going to do the same thing I did last time. We're going to define fun for function. Then we're going to undef it right after we're done using it, right? So this thing right here. But that way, like for instance, we've already typed it incorrectly somehow. And I don't even see where it is, but the other thing is not lighting up here. Here and here, they're somehow different. I don't even see how they're different. AAC, oh, ACC versus AAC. So I actually spelled it correctly up here, but not here. And I don't know, we'll just kind of, I guess technically, well, that's not even quite correct because one's hex and one's decimal, so there's not really equivalent places, like in terms of ones places, tens places, etc. Because this has ones, tens, and 100s, and this has like a ones place, a 16th place, and a 2 times 16 place, etc., etc. So I don't feel like there's a way to line these up in a way that would make sense. And I guess we should also check with, I don't know, that's probably good enough. I guess maybe if we really want to do something, we could do, you know, test that, you know, the min of these, right, 1 in the max, right? And that's all we need really for this kind of min function test here. Now this cap function, let's just copy all of this. And we're going to take I32 cap U32, which is kind of a very weird name. And unit test code, and then put the name right here. And then we'll kind of throw this in here now. So void, just be able to paste this, takes void. And this function is some type of cap function, but one of the unique features of it is that it's kind of wrangling types for us. It's there's different bit width, one bit width goes in and another bit width goes out. So it caps the int32 but it returns the u32. So let's kind of locally define a macro for this function. And let's also kind of see its usage and make sure that I know what I'm talking about. So we have an int32 that probably needs to be capped between a min and max value, it looks like. And oh, okay, yeah. It has to be clamped between the min and max. So if it's lower than the min, it has to be the min. If it's higher than the max, it has to be the max. But if it's in between the min and max, then we're good. So it's the input value, the min, and the max. And it's I32, int16, and int16. So what we could do is we could just take this entire thing and use those as our test input values. And then we don't have to think about naming new variables. And we can just kind of cut and paste, right? So int32, that's the brush value that we want to cap. And then we have the cap min and the cap max. And to test this, let's just say that if we have, you know, let's say the brush XY value is like 0x, and it's like, let's just put an F here. And I don't know exactly what number that is, but let's just, we know the range of an int16, and the cap min and the cap max are in that range. So we should do something like this. And then this we're going to expect no change, right? Because the max is bigger, the min is lower, so we're expecting no change, right? So for the first time we test it, you know, we're going to take the function, we're going to take the thing we want to cap, then we want to take the cap min and the cap max, and the output needs to be like the same deal, but it's a U32. So we could do U32, and let's just call it U32XY to keep it kind of simple. And then we will assert that, you know, assert U32XY equals 0x. We'll just take the whole thing, right? So this is the brush thing. That's what it needs to be equal to. For other things, we could get a little bit creative and be like, you know, assert that the function using, I don't know, 0, 0, and 0 is equal to 0, right? So something kind of simple. Assert that the function, if we have 0 capped between, you know, -1 and +1, then we also expect that to be 0, because it's within the range, right? And assert that the function, if we have a 50 between 0 and 100, we're also going to expect that to still equal the same value, right? So we're going to test some things that don't actually need to change. And then, I don't know, we'll figure it out as we go. Okay, and how about asserting that, you know, -50 doesn't change when it's between a min of -100 and 0, right? So we're going to kind of flip that on its head and assume that we're going to get the same outputs. And -50, we're going to expect a, you know, -50. Okay. And what other asserts we have? So we have things where the input's not changing. Tests where input doesn't change. Okay, so let's try like tests where capped to max value. Okay, so let's just copy all this. I'm going to change it to tests that are capped at the max value. So why don't we just try these inputs and then cap it at the max? So to cap this at the max, we would have to do like a -100 and a -50, right? And then, where they're capped at the max value. So 0 is greater than the -50. So we got the min and the max, so now we're going to get -50. To do this once again, with something simpler, I guess. The min is, we could say, -2 and -1. And then we're once again capped at the max, but this time the max is, you know, the -1. How about capping this at the max? So we have 50, we want to cap that at the max. Well, 50 is more than, it's more than 0, right? So we could do, you know, we could do 0, and -100. I feel like we've already done that. No, we haven't quite done that. We have a -100 there, but -100 is the min and this is the max, so we're going to cap that at the max. So we're trying to make sure that these two variables are all, these two values are the same, right? So for the next thing, min and max, so 50, so we have this -50, and we want -50. If we want -50 to be capped at the max, then we could just say that between -100 and say between 0 and, actually no, that's not a valid min, right? So -50, so -100, so 50 isn't as small as -100, but it is smaller than 0, so this would actually cap it at 0, right? And that would also be valid, right? So 50 between -100 and 0, it's over 0. Is -50 over 0 now? -50 is not over 0. I don't know how to math, it seems. -50 is less than... Hold on. -50 would get capped to 0 because it's less... God, I can't think with negative numbers sometimes. Okay, let's think about it. We want this value to be out of range to exceed the value on here. So 0 greater than -50. Yes. Is 0 greater than -1? Yes. Is 50 greater than this 0 here? No. Wait, yes it is. 50 is greater than 0. Okay. So what's the problem with this? Well, this is a -50. That's why I'm getting screwed up. -50 is actually greater than -100. Let's just make it easier on ourselves. And just do this. There we go. Here's our min. -200 is less than -100. -50 is not as negative as -200. But -50 is actually greater than 100, right? So we go 100. Well, hold on. Man, I just don't know how to... No, because it's not supposed to be in the middle. -50 isn't supposed to be in the middle of these two values. It's supposed to be over on the right, right? Because we're going to try to cap it with the max value. Okay. I just can't comprehend what I'm doing right now. So let's make sure these match, right? So the idea is that these values all match. And we're taking these values and we're just kind of capping them, right? Okay. So 4 more tests. So tests where capped to min value. So So if we really wanted to keep this as simple as possible, we could just probably invert these signs on everything. Yeah, I think we could just invert all the signs and we'd be good, right? Wouldn't we? Like, well, not this. Well, let's say 0 and negative 100. So this is the min. Oh, whoa. I can't flip these out of order here. So I see I'm kind of flipping things out of order here. And well, first of all, the min and the max are not signed at all. The min and the max are not signed, first of all. Second of all, do we have an assert function in here to make sure that the min and the max are not out of order? And we don't. So we should probably add that in because we're about to test it that way and use some bad inputs. So what happens if maybe when we're using the code, we're also doing the same thing, right? So we want to just assert that the cap min is less than or equal to, guess what? The cap max, right? Less than or equal to. Sorted / ordered. All right, want to make sure that data is sorted / ordered. Okay, so now that we have that assert in there, we've kind of caught how we're kind of improperly using these functions. Let's think about this, right? The min and the max here, we're not signed. Like, all of this is completely bogus. Well, not all of it. Anything where we have a negative. So this negative, whatever, let's just, you know, input doesn't change. It's a test where the input doesn't change. So how about 1, 2, 3, right? So 1, 2, and this is 3. And that means, oh no, sorry, 1, 3, and 2, right? So 2 is between that. Test where this doesn't change again. So 0 and 100, 50 is in the middle, doesn't change. How about 200? Just to make it easy. 200, and then we're gonna have a 100, and then a 300, right? So we just kind of use the same numbers as the previous test. We just changed the magnitude. And if the input doesn't change, then we're expecting 0 to 50 and 200. Okay, there. So that is proper now. And all these things, every one of these tests has a negative in it. So we're not even going to be like, oh, let's try to fix these. They're all of them are so wrong. It's just going to be better to cut, paste, start over again. So tests were capped to the max value. So if we have a 0, we can't really get that working, can we? Well, no, we can. We can still do like, you could be outside of the min and the max, right? So you're lower than the min. Ooh, okay, hold on. So if you are a value and you're lower than the min and max, well, you're outside of both the min and the max. Where do you go? Well, you're outside of the min and max. Well, you only check to see if you're less than the min or greater than the max. So you cap to whatever side you're next to. Okay, so that makes sense. So if we do something like this and you're 0, then oh god, no, not here. Down here. So if you have a 0 and you have like a, let's just keep on doing things with the same numbers. And you have this 100, 200. Well, 0 is on like the left-hand side of this 100, so it should be a 100. So even things as trivial as this capping logic, now that I think of it, I can see why we might want to. And that doesn't even cap it to the max value, does it? To cap it to the max value, it would need to be like 300, right? And then we end up at 200. We want to cap to the max here, right? We want these two values to be the same. So if we have 1 and 3 and want to cap that to the max, we got to make this like 4. And now that's a 3. So here, first of all, let's just take all these, right? We're capping to the max, so we're expecting these to be the same. If we have a 50, does that cap to the max or does that cap to the min? Well, it's inside the range, so it doesn't cap, it doesn't do anything, right? So we do the 200, and in the range 0 to 100, we're going to end up with the 100. If we have a 200 between this range, that's not going to cap it, so let's just make that 400. And okay, and that's not 400, that's 300. They got to match. Okay, so 200, 3, 100, 300, 200, 3, 100, 300, 300 between here. It's overboard. It's over this one. It's over this one. Over that one. Okay, cool. So now we want to take tests where it's capped to the max. And then we also want to do OOB cap to min using negatives, right? So we're going to cap to the min value here, but we're going to use like positive values. Like all the values, all the inputs are going to be positive. In order to get that, we could just kind of move everything to the other side, right? So we could take this and we could make this a 50. This could be a 0. This could still be a 0. Why not? And this one right here could be a 50 as well. And then we can take all of these, right, because we're capping to the min, and that's what we expect, right? We expect it to just be all of these this time. Less than, or less than or equal to. Okay, so now we're going to take more tests. And we want to cap to the min using negatives, which means that all of these inputs, we just want some negative inputs. So, you know, negative 999, and int 32. I don't know. How about negative 1, 2, 3, 4, 5, 6, 7, 8. Are we still in the range? So this is 1,000. So we got like 12,000. That's plenty of precision even for a 2-byte value. So let's just kind of stick with that. And then we can do, you know, 2, 3, 4, 5, 6, 7, 8, 9, right? 3, and then we can do, you know, 3, 4, 5, 6, 7, 8, 9. 0, I don't know. Roll over, I guess. Then we can do, you know, 4, 5, 6, 7, 8, 9, 0, 1. Okay, so cap using negatives. We got our nice little asserts there. That's a decent little unit test. And we only use these variables in one little place here, just to formalize the first time we use the function. I just wanted to kind of, well, first test to formalize what the parameter names we are working with are, right? So this is kind of hacky, but the idea is that I want to be able to read the code without like using IntelliSense or anything. So I'm gonna just be able to look at this and be like, oh, it's this, it's that, and that, right? I can tell that this is the brush location. Now the brush XY, oh, it's the brush X or Y, that's what that is. Brush X or Y location, right? It's a brush X or Y. Minimum boundary. This is the minimum boundary. And this is the maximum boundary. And this one here is just a uint32 value. U32 output of function. Okay, that's good enough for me, to where I'm like, I am satisfied with those little summaries. I don't feel like writing test code, but at least it's not too hard, right? I've come down from drinking a lot of coffee on Monday, and then coding into Tuesday. Okay, so now we have a test for this little cap here. So let's kind of cross this one off and just kind of meticulously go through everything, right? This is going to be, we're writing so much code without testing, without recompiling. Like this is gonna be a pain once we start trying to compile. Cancel. Okay, so astpix to diagpix. Let's take that and make that into like a little function. So take this and paste this again. Take the actual meaningful part of the name and put it after the UTC here. All right, just paste over there. Then take this and actually start writing a function. So it's also going to be void. We don't really care about returning a type from it because we're just going to crash at runtime if it fails. We're just not even going to worry about it. Okay, so astpix converted to diagpix. Well, first of all, astpix and diagpix, what are they? We can look at our diagram. And I believe astpix to diagpix. Astpix is like any type of pixel in this area here. So that means that the diagonal pixel is what can be, if you want to do like a simple back and forth kind of test with this, we can go diagpix to astpix to diagpix, but we can't go the other way around, right? Because there's, when we're pigeonholing this, there's less diagpixes than there are astpixes. Okay, it's good to know. Now that we've looked at that diagram, we can take this, and let's kind of keep on doing our convention of, you know, inside here. We're just going to define the function we're testing, paste it down there, and then once we're done with the function that we're testing, we're going to put it right there, right? So that's so that when we call it all over the place, we, first of all, this is really long, and second of all, we don't want a whole bunch of calls where it's like, oh, we saw another instance of this, oh wait, it was just in a unit test. You know, we don't want this call to be all over the place in our unit tests, cluttering up our ability to follow the logic of the program. Okay. Let's take... So, how about for diagpix equals 0, very similar to, in fact, let's find the 4 for the other thing we did, because we can probably pretty much take this kind of thing here. We can probably take all of this kind of logic, instead of having to rewrite it, we can just paste this here and just change things. So we're going to start off with diagpix, so things are going to be shifted around, and also if we see the function, this is a back and forth. Oh, wait, hold on. So I see, we have a astpix to diagpix, but we don't have a diagpix to astpix, do we? Why is that? Because it wouldn't make sense. Diagpix technically is an astpix, but astpix is not necessarily a diagpix. I see what we're doing. This is kind of like a, diagpix is kind of like a flourish style function, now that I see that. Okay, so let's not do this. My bad. Let's just do some asserts. So let's do asserts with like the basics of this. So this 128, assert that if we take this function, where we take 128, let's assert that 127, that's going to lead to 0. But if we do one more than that, 128, then that's going to give us 128. It's going to give us the next origin value, right? If we go a little bit overboard, if we use, let's take 128 and add 128 plus 64 minus 1. If we do this, we're almost in that next cell, but we're still not, so we get 128. If we plus 0, instead of minusing 1, we plus 0, then we're going to expect to be 128 plus 64. And what is 128 plus 64? You know, equals... do we want to put it as 128 plus 64? Or do we want to use the actual... God, fuck this. You put 128 plus 64 and it's like blood pressure? How about, let's take Google here. 128 plus 64. 192. So we want to put 192 in here, or do we want to put 128 plus 64? Well, here's an idea. How about we put 192, and then we also put this as well. Right, we could do that twice. Like maybe we want an explanation of what that value is, so we do the same test twice. You know, we could assert that, you know, we could assert that this equals 192 as well, right? We could get kind of crazy with that. We could get a little bit overboard here, right? And let's say assert... What else do we want to assert here? There's a lot of things we want to assert. So 128 plus 64 plus... What's the next power 2? 32 minus 1. So the idea is that this next one we are still hoping to be, what do you say? We're still hoping to be in that 192 area, right? And then when we do plus 0, we're going to be at that next thing, right? So we're going to be at, we're expecting now that this is going to be exactly equal, that we're going to be plus 64 plus 32, right? We're expecting this. And I don't know how to organize these columns very well. Okay, what next? Well, let's make sure that if you add a single 1 to it, right? We're trying to test the edge cases. If we add 1, we're going to expect to get the same exact thing. So do we have a... we have a minus 1 and plus 0. And we did not have a plus 1 for this, right? So we should duplicate this right here. We're going to duplicate this. We're going to do a plus 1 right here, right? So 128 plus 64 plus 1. We're still going to expect to be in the same 128 plus 64, right? You can also remove the plus 0, sure. Remove that. Okay, what's the next thing we want to do? Well, let's just keep on doing it. So plus 32, what's after that? Plus 16, right? And if we add 16, let's minus 1 to say, hey, we're going to test the thing right before that. So we're saying that we're still in plus everything. We're still in the same range of these three here. But then if we do plus 0, right, then we're in the range of, you know, plus 16. And if we plus 1, right, so instead of minusing 1, we plus 1, we still want the same thing. Okay, now what's the next thing after that? So 16, how about plus 8, right? So the next power of 2. If we use this power of 2, but we minus 1, we still want to be over here, right? But then if we plus 0, then we want to be plus 8. Okay, and then if we plus 1, same thing, we're still in the same range. Okay, so now we're kind of running out of room So let's kind of collapse what we have going here, right? So let's take the same exact test. So we're going to say previous test, but collapsing numbers. So we can don't run out of column space in source code. Right, so this is specifically for formatting. We're going to take the exact same test because we just want to make sure that, you know, if this is the test we want, then we want to make sure that the 249. We want to make sure that, do we just do, yeah. So let's take this, paste it down here, and this is 249. And then over here on this side, I'm putting this in a calculator. I do not know, I would not be able to do this in my head. Is 248. 248. Does that make sense? Yeah, because this is one overboard. And the other thing we might want to do is we might want to make sure that we know that this test case here is kind of special, where it's like hashtag don't touch me. Okay. And we just want to yeah, so something like that. And then we're going to continue doing what we're doing. But we can start back kind of here. All right, we can take this and say, you know, okay, we got this 249, and that equals this, you know, 248. And why do we have this extra space here like that? That doesn't make sense. Yeah, okay. So these should also, we're just gonna do it like this once again, and then now we're gonna duplicate it. So there's a little bit of excess calculation. That doesn't matter. It's a unit test. We don't expect it to be super efficient. So 249. Well, actually, we don't want to use this value. We don't want to use this because this is the +1. We want to start off on one of these comprehensible boundaries here. We don't want this +1. I changed my mind. Redo it. We're gonna use this previous one because it's going to be easier to think about this if we put that thing with the +1. Everything is going to be weird land, right? And these are both the same now, right? These are both the same value as well, so it makes it a little bit easy. Yeah, this is 248 and 248. Yeah, let's do this 248 and 248. Put it here and here as well. Okay, now we're gonna take these guys and be like, oh, okay, so this is the +8, right? We're in the +8 section. So now we want to do something similar, but we do a +8 or a +4, right? The next power of 2 down. -1. And if we do that, we're going to expect to be, oh, we're in the same section, right? And now if we do a +0, well, same section as well, because it's still 248, which is kind of weird to write it that way, but we know why we're writing it that way, so that's fine. So this next thing is going to be 248 plus this power of this 4, right? Plus this 4. And we're running out of room. Right? We're running out of wiggle room. So let's do this next one. So we got this +4, +4, +1. Hold on. +0. If we +1, it's no longer +4. Hold on. 248 +4 -1. We're at 248. If we do +0, we added the thing, so that's +4, right? If we add 1, we haven't gone out of bounds yet, so that's still this thing. And then this thing, if we do a +2, if we do a +2, we're out of room to wiggle around, I think, because +2 it's getting too close. So we're just going to say, if you use this value, then we're expecting you to be right here, right? Now, what if you're 1 less? If you're 1 less, we can still do... No, that's pressing it, right? Because this +1 already gets... Yeah, we're getting too close to that one single pixel. So let's just do the rest without let's do the rest without any of that wiggling around that we were doing earlier, right? So let's just, if you use this value, you get this value, right? So it's not... Yeah, that's fine. That's enough. That's enough that I'm, like, happy with it, that I'm not concerned that it's wrong. However, we might want to say, we might want to use an explicit value. Use some explicit edge case values. Okay, so what about 0? Is 0 in here? We don't have 0. We don't have 0, huh? So let's say assert, fun, and we use 0. Well, we're going to expect that to equal 0, right? I mean, that's kind of an edge case. And let's use the upper edge case as well. The upper edge case would be 255, right? Or actually, it would be 256. But we should never get 256. 256 should be out of range, should it not be? 256 should be out of range. However, if we get it, we get it, right? So if we do 255, then that should equal 255. That's our one little pixel, right? Our one pixel gets us that. 256 should be out of range. But also, if it's 1 pixel, then the 254, that is also 1 pixel, right? But there's just there's 3 of them, right? So that should also be 254. Or is that correct? No, because it's the 250... No, 255 is 1 pixel. And it's useless. Like, we should never use this. So, should never use. So if we... So let's just make a note here. If 255 fails because it is out of bounds, then just comment out that test as the case has been properly handled by runtime asserts in the function being tested. Okay, so just making a little note here. We don't ever expect to use the value 255. 255 is the last pixel on a 256 by 256 canvas. It's that useless pixel that we never have any use for. So 254 and 254 are our 3 pixels. And that still means that if we do assert fun 253, what should 253 give us? It should give us not 253, we're going to have 2 by 2s, so it should be 254 minus 2, so that should be like something like 252, right? Minus 2, I think. Okay, so that's what we kind of think it is, and if these tests fail, we can always check to be like, is the test code wrong, or is our assumption wrong on how that's supposed to work? So, okay, we got test code for that. So we are kind of like flip-flopping between test first and code first. But it's just like I want to clean up loose ends as right, there's loose ends all over the place. It's like exploding, like the mental stack space, which as Uncle Bob of Clean Code would say, you don't have a mental stack. So that's the problem, because we're juggling around a whole bunch of things. But yeah, aspix to diagpix, that's good enough. We're good enough there. So let's copy all of this and do another test. So here we're going to have this glockpix to painpix. And not like that. We got to take the important part of the word and really we don't need two test functions for this, right? Because we're going to test back and forth. Well, we could do glock to painpix to glockpix, and the other one could be painpix to glockpix to painpix, just for the heck of it, I guess. So let's take this, and let's also make the other function. Let's make these kind of in parallel, I think. This could be a bad idea, I don't know. Okay, so we have these functions. Let's make use of them. Okay. Void. Taking void. Do something with that. Then we need the other one, so we could just take this, copy it, paste it. And then just take this function name. And we want to do these ones together. I'll just call these paired unit tests, right? Paired unit tests, because that's kind of what they are. And then we can take this, we can put it over here, and we got way too fancy with this. So we are, yeah, what am I doing here? Well, I'm committed to the design of this, so let's just, you know, if we really want to do this, let's do it. Okay. So paired unit tests. There we go. So now we have, yeah, we have these two sections, and then here we'll do dash line I to x64, right? So we'll make a little dash line in between these two things like this, but these are kind of like paired unit tests. Okay, because they are symmetric. Okay, so glockpix to painpix. Well, let's look at what glockpix and painpix are. And what do we got? I don't know, I'm kind of tired of this. I'm kind of sick of this. I mean, it's been almost 5 hours, but we really should put in 8 hours. Even though I'm kind of sick of this, we should put in at least 8 hours. So glockpix to painpix. I need a break. Maybe I should do some push-ups. So we have glockpix here. Do we have it in the diagram so we can kind of easily see what we're looking at? So we don't. Great, 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 great. I think glockpix is just a global TX, global TY. Yeah, it's just the global TX, global TY. So if we want to think about glockpix, what we could do is we could so I like keeping these two diagrams up here near the top. And then we have all this other stuff, blah blah blah. Let's just put the next thing down here. Paste this here for a second. Oh, still not enough room. So I think this is too long. We're just trying to conceptualize glockpix and painpix. I think it would make sense to make something a little bit smaller here, where we kind of, if we could just kind of use this square here, maybe, and use that to represent our 512 by 512. So we have it, and let's take it and kind of use this to represent. We're going to use this many, and we're going to this will represent 512 by 512. So we're going to like kind of condense all of this. So this is going to be 512. And now over here, that's going to be 256, and then the 128 is going to have to be even less than that. Insert. And over here, this 128 is kind of like to this midpoint here. Like that. So when we're talking about Glock picks, oh no. You say, you know, oh, we put some G's in here, right? I'll just say that, you know, Glock picks is literally like any point in this subdivision, right? So G, it's going to be Glock picks. G equals Glock picks. G equals Glock picks.x or whatever. I think right. Alright, so G anywhere is we're basically saying Glock picks is like a global value anywhere on our 512 by 512 texture, right? And if we wanted to, we could go into pix name really quick for a refresher and take that variable, this guy right here, and we could make a note that, you know, this is, we already know we're in this library, so we could actually take that away and say, you know, when we're looking at right here, this thing right here, what are we looking at? That's what we're looking at right here, right? Right, pix name, CPU pix, that's what this big deal here is, right? Okay, so now that we have some type of reference point where what Glock pix is, well, okay, if that's Glock pix, then what the heck is pain pix? And pain pix equals, do we have pain pix in the little index here, but I don't think we have it anywhere else, right? So let's take all of this as reference. Let's paste it down here. And just say, oh, no. If we have something like, now let's move this up. Okay, no, Control C, Control X, or Control X, that works. So let's take this and let's divide this into a section. I don't know what we're going to call this section here, but we need some type of, I don't know. How about, dia lockpicks? Right? Or, glowpicks? Dia glowpicks? Dia glowpicks, or we could also call it, dia glockpicks, right? Just so we know what we're talking about either way. And then we can seal it off on the other side. Okay. So the reason I wanted that, I just wanted a little bit more room. Because when we chisel away at this, so let's say we take just this, let's say we just take this G here. Or how about not just this G here? How about we take this G here? Let me think about it. Sure, that would probably be the easiest for our example. So let's just take this G right here and just look at that for a second. And say, when we're looking at this G, the tile exponent equals 0, right? And that's no matter what cell we're looking at here. Oh boy, that's no matter what cell we're looking at. We have this equals 0 for the tile exponent. Okay. But over here, when we're looking at here, this is I think it's tile qua 0 and til qua equals 1 here, right? The quadrant. Well, actually, no, we don't know what exponent size we're in. We're still dividing by the quad, right? Because we're zooming out by 512. So these are actually the quadrants. The tile exponent is actually wrong. We don't actually know what that is yet. Okay. Then if we take that again, and we're like, man, we want to know what the exponent is. We can take this diagram. We can paste it down again. We can kind of chisel away at more of this, and we can say this G right here, we can chisel away at this G here. We can kind of subdivide here. And we could also maybe, in this section, we could kind of make it dots or something maybe, just to make it more obvious that which section we're looking at maybe. And the tile exponent here is also 0. So, so tile exp equals 0, right? Something like that. The tile exponent equals 0 for G. And the tile layer, is actually 0, 1, 2, actually, are we? Yeah, the tile layer, we already know the tile layer, right? We figured out the tile exponent. And the tile layer is, okay, it's not the best example, right? The tile layer is, no, 0, 1. The tile layer is 1. So now we hit this, and we also hit this, right? Nice. So we could also say that, you know, the local TX is greater than or equal to, we're in the first cell. We're in the, in terms of globally, we are greater than or equal to, this is 512, this is 128 here, right? This is 128. Or is it? Or did we, no, yeah, because we just chiseled away at it, so, so we're greater than or equal to 128, and, loc tx is less than or equal to this divider right in the middle, 256. And then let's make an example for what the y values are. So the y values are a little bit different for the local value within the cell, because it's oh, actually no, the local value is, what am I talking about? The local value is not gonna be between, that's this global value. We're looking at, this is the global. The globals, right? We could look at the globals though. The global ty's is greater than or equal to, it's greater than or equal to 0. And it's less than or equal to this 128 divider, right? 128. Yeah, because this is 128 right here. Because it's also 128 here, right? Right here is, you know, our 128. I don't know if we just want to do this so we can kind of, it's not quite symmetrical. If we want to look at the locals, though, so let's take this global and think about the locals, though. What are the locals? Maybe we want to be kind of nice here and be like, make a nice little diagram. I don't know. Okay. So for the globals, we've kind of figured out the globals here. They're right kind of here. So when we're looking at the locals, let's divide this so we kind of know. So that when we're looking at this, we want to be able to know if we're looking at globals or locals really quickly, or we know that this is one different group here. So global xy's. And right over here is, you know, local xy's. Okay, globals, and so we're going to rename this to local. And then we got to think about, well, what is that local? The local tx and the local ty. The local for this outermost tile exponent is just between 0 and 128, right? Because this is, or not 0 and 128. Let me think. So we're here. We kind of have to figure out which one of these guys we're in, right? And then we have to subdivide by the tile exponent size. And we're at tile exponent size. We're at tile exponent size 0, so that should be 128. So this should be just 0 to 128 for each one of these, because it's local. So there's no change on the x or the y. So now I'm curious, did we get that correct? Let's put some breakpoints in here, because we haven't finished this. Do we have that correct if we're looking at, do we have any tables or anything in here that already give way to that, like, 128 kind of a thing? We have a thing called max core, don't we? Max core. And in the conversion function, yeah, we have 0 to 127. Ooh, 0 to 127. My bad. So, what we could do... God, we have breakpoints all over the place. Okay, so that's my bad. It's not 128, it's actually 128 minus 1, 128 minus 1, C, you know. If you want to know why we have that maximum coordinate, you could see this function and you would know why. So diaglopix, right? So now we have any variable, well, not any variable, but most of the variables that are in this index over here also have a nice little diagram that tells us what it's all about. Not all of them, but a substantial amount to where when I want to know what I'm looking at, I can see that. Now, we don't have a title for what this is. Dia selected, so this is just diag. Let's call it diag, pix, and local. Diag, and local. Sure, why not? We'll call it diag and local. Because we just want to give it a name so that if we ever want to reference these diagrams, we can just be like hashtag diag and local, and we know what diagrams we're looking at. So every kind of section here has some type of name associated with it, right? And so I don't really see a reason for why we are doing this kind of thing here. We're kind of like double burying, right? We have this big multi-line comment. Let's just keep it as one giant multi-line comment for all of the diagram section, and then another multi-line comment for actually no, let's just get rid of that. So let's just call this hashtag PAINT5D index list comment. Right, we'll call it index list comment. Sure. And we will kind of like inline that, right? Yeah, let's not make all these multi-line comments when we don't really need to. And then we can label that section as the index comment. And then up here at the very top, we should probably name this something. How about PAINT5D data layout versus what artist sees? That is quite the name, quite a very long name. But for now, until we need like to actually quote this section somewhere and we realize, oh god, this section is way too, this name is just ridiculously long, until we realize that, oh god, the section is too long and we need to give it a shorter aliased name. Until then, this will be a good name, right? Because we have what the artist kind of sees. The artist sees these 4 gigantic tiles in their viewport, or maybe they can zoom in on one of these or the other ones. So this is the basic setup, depending on how the camera is working. And this is the actual data layout. Okay. Yeah, that looks good. So we've kind of organized that, and we still don't have any running code because we just have way too many loose ends. This is stressful. Okay. Well, let's just look at GlockPix to PaintPix, right? So we can look at GlockPix is just global pixels. So I might want to make a note here that glow tx equals glockpix.x. Same thing with y. I just want it there as well. The reason I want it here as well is so that when I am looking for the global pixels here, I can just go like this and be like, oh, we should probably highlight GlockPix as well, so that we can see those things in the diagram as well. And that way when we highlight those, I can be like, that looks relevant, right? And we can look over here and be like, this is also relevant. And when we scroll up here in the diagram, we don't see any of that cyan. We just see it over here. We're like, okay, this right here, this is the diagram we should probably be looking at as we're trying to write the tests. And I see that I'm missing something. I'm missing the big list of what PAINT5D is, right? Because we have that's all nice, but we have a little room to here to kind of cram that in there. So we can see PAINT5D, pain pixels. So I'm going to take this and do PAINT5D dot right here somewhere. I don't know, like here. Now we could indent it one more time. Yeah, so something like over here. And say like PAINT5D dot. And then we could do like a little dot thing. And then maybe we want to indent, I don't know. Dot. Actually, let's do this. 1, 2, 3. 1, 2, 3. Or we could do star, star, star. Underscore. Star, star, star. Right, the idea is to have this kind of, it's a wild card, right? I don't know if I like that. I think maybe a, like, strike through. And then down here, we could kind of keep that same thing going like here, like this, like. Yeah, I kind of like that. That looks kind of nice. And then let's fix what we messed up over here. Yeah, so PAINT5D, so we can kind of see like the relationship, right? Because we have this here, and then if we do this, we can see it here. And any of these things we can see have a thing that's going to light up when we look at this, right? So that way, right, because the conversion is GlockPix to PAINT5D, and PAINT5D is actually all of these different, you know, things. I don't want to do this. Okay. Do we have any, like, backslashes or characters that shouldn't be in any of this? Oh, we do. We're doing something where... Yeah, so this got to go. Yeah, these are going to screw us up. And I don't know how we're going to fix that. Here's what we're going to do. D, we're going to change this to D, Ds, and Ds. And just see D diagpix. Right. Over here, D diagpix. And it's not quite as good, right? But it's just because if we have these slashes in the code, in a multi-line comment, I know that they usually kind of cause problems. It's either the forward slashes or the backslashes. But let's not take any risk here. So anywhere where we see, okay, tile quad, we don't really need to point to the center, or do we? Tile quad is 0, 1, 2, and 3. It actually is representing this kind of whole thing here. So let's just remove this. And, you know, tile exponent, and we might want to, let's just do another one of these things here and just be like, this is, right, this is a tile qua 3 here, right here. This is at tile qua. We could just put a 3 here. We could put 3 here and hopefully we know what we mean by that, right? And I want to keep these arrows kind of next to these two diagrams, so I'm not going to try to do more than that. The next thing we want to do is let's just, outside of here, really quick, let's, ooh, yeah, that's going to create a problem as well. So we already have these kind of things here that can kind of, this is inside a multi-line comment, so we cannot be putting a comment inside a comment, first of all. So let's look for this character, and we also want to look for this character as well. We want to, anywhere we see any of these characters, actually let's make them orange, because I think that's going to be easier to find. If we find this character or this character, down in here, we got to remove it. So look for anything that's glowing orange, and if it's inside of if it's inside here, we got to use something else. Cell partition. I don't know what to use instead of a slash here. We could use an or. It's not quite the same thing. I don't know. Just anything but that slash, right? Right here, we're outside of that multi-line comment. So we don't have to worry about these. We're good. We're already outside of it. It's just that one thing would have screwed us up. So there were a few things that would screw us up, but we got rid of those. So right here, instead of kind of doing that, well, we don't need this. We can kind of, this video comment was pretty useful. You can just put it in a nice little box, right? Be all designy about it. Have people yell at us because we're taking too much time to design the comments. Okay, good. Okay, I really don't... yeah, I'm kind of tired. I don't want to... I don't know. Yeah, so let's look at this diagram. And first thing I want to do is, well, find the actual functions that we're going to use. So these beefy boys we need to use. We're going to take that signature, go to the function that we need to test, and be like, this is the thing. This is the thing we need. We can instead of so right here, we can use this to create like a list of things we're going to need. And some of these aren't going to be pointers. We're not going to declare things as pointers, right? So we're just going to use this. And then we can call it okay, I'm not going to worry too much about that. For this, we could say, we could say what diagram to see. So we have a diagram. We have a suitable diagram for what we need to see for this. So for all these different things, the tile quad, the tile exponent, the tile layer, the local, all that stuff, this diagram makes the most sense, right? So we could say, we could see, C and hashtag diaglopix. Dia stands for diagram, by the way, if that wasn't already obvious. And we could just make a nice little comment here about where we're supposed to go. Where are we going to find this information? That's not exactly where I want this to be. Just kind of throw it in the middle there. That looks a lot better. And yeah, my brain's not quite working here. I think here's what we're gonna do. I'm gonna do some more push-ups, and then I don't know. I think I just need to take a break or something because I'm not quite energized to do this. So yeah, let's take a break because we're going too slow here. I mean, we're kind of like doing a little bit of maintenance here and there. We're like, procrastinating, fix up some diagrams, procrastinate, fix up some diagrams. I mean, the diagram work is valid. It's just that, hey there. I'm still feeling the effects of having done a whole bunch of coffee on Monday, so I'm not totally all here. Yes, I will. Yeah, I think, yeah, push-ups and then, yeah, okay. Yeah, you've been listening to me. Yeah. Yeah, I'm just gonna do some push-ups and, because I'm trying to do like 10 per hour, which isn't much, but, you know, whatever I can do. And then I'm thinking I'm gonna try to keep on writing these functions, but I'm just like, I'm just not feeling it right now. But yeah, okay, yeah, I got you. Hold on. So we're at 5 hours, so we need at least we need at least 50 total. So let's see where we are. So I only need 10, but I'll try to just get 20 done, because I think I can do 20 in a row. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and then just 2 extra for good measure. Okay. Sounds good to me. Burgers are awesome. 5 more. Yeah, I'll here's what I'm gonna do. I'm gonna think about my life, and maybe I should just watch some YouTube videos for a second. I don't know. I just feel like it's like when you know what needs to be done, but you're not doing it. I think that's where my brain is right now. So yeah, I mean, look at all these diagrams and things. It's like, whoa, this is crazy. Oh god, it's not just that I don't know what needs to be done, or that I know what needs to be done and I'm doing it. It's just that, man, you get overwhelmed because you have all these loose ends like all over the place, and you're like, fuck, man. I have usually writing good code. You want to write a little bit of code, run it, write a little bit of code, run it, write a little bit of code, run it, and not like, but every once in a while you totally fuck that up and you end up with like a whole bunch of loose ends because there's so many like interrelated pieces all over the place, and you're just like, fuck, I'm fucked. So we've kind of like, we've spawned like, you know, many different threads with many different, you know, things that need to be done, and yeah, so, oh god, just but it's gonna be awesome. I'm getting really close to having something ready for my artist. I'm thinking, you know, optimistically or like conservatively, because I know how long this takes, probably like 1 more month maybe. I'm going to start to get some cool visual stuff going, because this is the layout for the editor. This is the layout for the data in the editor that he's going to be using. So anyways, yeah, you go grab a burger. I'm gonna think about if I want to start a new stream. I think I'm going to start a new stream just because I don't want to just have a stream where there's just a big break section, and I think I need like an hour to just not do stuff. Yeah, but I'll see you in maybe an hour. Yeah, I'm gonna end the stream and I'll be back here in like an hour and try to like get some more stuff done, because the idea is, if I'm awake and my brain is not, it's not like my brain's completely totaled. If my brain's not completely totaled, I don't want to just waste it on, you know, being completely lazy. I want to actually, if I don't have all the motivation I want, but I have enough mental energy, right? Like, that's the problem. Getting everything, mental energy, motivation, getting all those things to synchronize at the right time, almost impossible. And that's why I have the Mondays where I actually drink coffee, and just Monday is guaranteed that I have the motivation and the brain power, and then every other day is kind of like up in the air. So yeah, I'll see you when I see you. Good seeing you here.